So our topic for this afternoon is about load schedule and voltage trap calculations. No, so uh, there are a lot of actually there are already a lot of presentations about this one. No, so we might be wondering why they always go hand in hand, yung load schedule and voltage trap calculations. No, so just an overview. These two aspects of our design analysis is pretty related, no? Kasi yung load schedule natin, the purpose of which is in sizing up, no, our conductors, our protection devices, and yung si voltage drop din is also one of the elements, no, in sizing up, no, our branch and circuit conductors and feeder conductors, no, so actually sa TER kung may yung nag-apply na for PEE, yung sizing of conductors natin or circuits natin, no, hindi yan ma-complete sa yung calculation lang, no, sa load currents natin, but also we have to evaluate also, no, the voltage drops at certain points in the system before tayo talaga maka-finalize dun sa sizing of conductors natin, no? And together with also the short circuit withstand, no? So tatlong elements yan. So these are just two of those three elements, itong si load schedule and voltage drop calculations, no? So with that being said, kasi hindi natin sinama si short circuit kasi it's a entirely a topic of its own because of its pretty comprehensive, no, medyo mataas talaga, no, yung calculation process ng short circuit calculation, so it has to be treated as a separate lecture, no. So with that, let's proceed, no, with our topic this afternoon. Okay, so yeah, this is our outline, no. We have to discuss some objectives, no, in our lecture, what are learning outcomes after this lecture, no, and we have to give some introduction, no, why the importance of these calculations and what are these requirements, some definition of terms para during along the discussion, no, we'll be familiar with some of the terms that we'll be using, no, and the design references, and also design considerations kasama na rin. Ano yung mga general design considerations para yung during the designing natin, may guide na tayo, no? We have to set our design boundaries as per code requirements. Then the development of load schedules, how to develop this one, no, starting from the design analysis talaga, no, uh, and bago tayong maggawa doon sa actual talagang mga calculation process natin, no, the branch circuit sizing, the feeder circuit sizing, the overcurrent protective device sizing. Then for the second part is our voltage drop calculations, no, so we be presenting the prescribed limitations as per PEC 2017, no. So by the way, yung dapat gamitin natin na reference is the updated code natin, not the previous outdated, no. We have to use the latest edition of our Philippine Electrical Code, no. And the methodologies of these calculations and system modeling. So this is very important, no? How we model our system kasi diyan natin talaga magsisimula ano yung mga impedances, ano yung configuration ng circuit natin. So kung nagkamali tayo diyan, medyo inaccurate na yung calculation natin. Okay? Then the actual calculations of voltage drop, no? Okay? So uh, let's run through lang shortly with this discussion objectives, no. So ito yung mga dapat nating expected outcomes. So dapat malaman natin ano yung purpose, no, bakit tayo magawa ng load schedule. I know a lot of us have already been familiar with load schedules, no, but siguro some additional points na lang, no, for emphasis, ano yung ibang uses, no, or ano yung benefits na maibigay ng isang load schedule in terms sa Marami to in terms sa construction, no, in terms during implementation, and also for our suppliers and manufacturers, no. It can serve as a guide. Malalaman natin mamaya, no. And then we be able to be familiarized with the requirements during in the preparation of a load schedule. So marami yan. We'll discuss later, no? What are those? Para talagang yung paggawa natin ng load schedule, medyo accurate yung mga data nating ilagay natin sa load schedule, no? And then developing a comprehensive load schedule, no? So in various load configuration. So pwedeng single phase line to line loads, line to neutral loads, anong difference ng among these different configuration, no? May mga kuan lang, mga slight variations lang into the calculations sa iba't ibang load configuration, no? So three phase data connected load, so ito yung connection na yung neutral natin ay isa lang, no, or fourth wire natin, fourth conductor natin serves as equipment ground conductors lang, so wala tayong connect loads from line to neutral. And the three phase Y connected loads, ito yung may neutral, no, line to neutral loads, no. So ito yung mga 400 volts to 30 volt system. Okay, so let's move on. And for the voltage drop, so we may be able to understand the principles and applications, no? Malaman natin bakit importante ma-evaluate natin si voltage drop in the system. Ano yung effects niya sa system, no? So that during design, every design natin, hindi na natin ma-taken for granted si voltage drop. May talagang impact si voltage drop, especially doon sa mga life safety equipment natin like fire pumps, no, and other sensitive electronic equipment, especially in healthcare facilities, no, na yung mga equipment natin sa operating rooms, no, medyo sensitive sa mga voltage variations, no, kung hindi natin ma-stabilize yan, no, pwedeng malaking impact na yan sa mga pasyente natin, no. So dapat i-address natin yung mga severe voltage drops natin, no. Okay, so yung malaman na natin yung requirements as per code natin, and then the different methods. But this one, I'll just be discussing about lang dung sa approximate formula natin, no? Kasi meron tayong calculations din presented in our Philippine Electrical Code, but may slight difference lang, no? So depende lang sa saan tayo komportable, okay? And then we be able to finalize the branch circuit and feeder cable sizing. So, yun yung sinabi ko kanina. Initially, meron tayong ma-establish na conductor sizes natin, no, dun sa load schedule. But it is not yet the final conductor size. So, we have to evaluate the voltage drop kung kailangan ba nating i-upsize kung hindi siya compliant dun sa prescribed voltage limitations. No, so, yun yung second consideration natin during circuit sizing, no? Okay. So dapat natin tandaan 'yan na hindi enough yung na-arrive natin na circuit sizing during dun sa load schedule. Uh, I-follow through na natin din yung voltage drop calculation to be able to evaluate further kung hindi ba magka-problema. Kasi yung voltage drop is dependent on the conductor size and the length, no, of the conductors from one point to the other. So malaking impact yan. Okay? Okay. So some exclusions lang sa lecture natin, no? So this will not cover short circuit calculations, protection coordination. So alam natin may separate speaker natin dito natin ngayon, but unfortunately lang wala siya dito. So may emergency. So separate topic talaga. And then power flow analysis, grounding system, although may touch akong basic, no, sizing of equipment ground conductors, but yung grounding system calculations hindi kasabay dito, no. Okay, nagchat choppy. Siguro sa signal ko. Anyway, sige, paki-feedback lang po, no, kung para ma-check ko yung connection ko kung ako ba talagang may issue, no. Sige.
Sige po, Gov. Isabihan po kita.
Sige po. Thank you. Thank you. Thank you, sir. And then hindi rin kasama yung fire pump sizing natin, no? So, yung fire pump is an entirely separate topic on its own kasi may ibang design approach din si fire pump, no? Medyo it contradicts with the normal concept natin of circuit sizing na dapat maproteksyonan yung circuit natin. But si fire pump may ibang consideration 'yan, no? And power factor correction hindi kasama. And wala tayong ipakitang mga electrical layout plans, although pwede nating gawing guide yan, but for this one specific tayo for load schedule. Okay, so let's start. Okay, uh, okay, move this away. Okay, so ano si load schedule? Then let's get to know better, no? So basically si load schedule or schedule of loads, no, is a summary or listing of data of the following, no? So the electrical system parameters, so yung power in kVA, yung nominal system voltage natin, no? So in the load schedule natin, usually ang ginamit na ang reflect natin is the nominal system voltage, no? Hindi si equipment voltage, no? So nominal system voltage, so kung ano yan, yung 400 volts, 480 volts, 230, ito yung mga nominal voltages. So magkaibang convention lang. Si 480 is saan si kuan yan, saan si convention, no? Si 400 to 30 volts is IEC, no? Ito yung common natin sa mga bagong kuan natin ngayon, mga establishments, no? Electrical system. Si 400 to 30 volts, especially for high rise. Si 480 to 230 volts, ito yung medyo mga naunang systems natin, no? Adapted ito sa ANSI, kuan, standard convention. So ito yung may transformer na step down transformer from 480 to 230 volts na mga small power loads, no? So ngayon, we adopted IEC. Ito yung si 400 to 30, may neutral loads na ito, line to neutral loads, no? Yung mga single phase loads natin. So advantage of this one, wala tayong need for step down transformers, no? We can utilize, no, the neutral connection to get the phase voltage of 230 volts to supply the single phase loads natin. Okay? So I know familiar kayo dyan. Okay. And then also some of the parameters is the current or load amperes. And next is the electrical equipment ratings. No, what are these? Equipment ratings of wires and cables or conductors. Yung sizes nila, cross-sectional sizes or wire gauge. And the overcurrent protective device, either a fuse or circuit breaker, yung nominal rating nila. And also the interrupting ratings, no? Kasama na dyan. Okay? Ampere trips also. And the conduits, their yung kuan nila, mga diameters nila, no? So, what why do we really need to prepare a load schedule in the first place, no? So ito yung kuan, ito yung mga benefits na bakit talaga ni-require, no? So it's a standard requirement, no? And then the benefits of such is it helps in determining the demand, no, or power requirement of a certain electrical installation, no? Kasi pag hindi natin na listing 'yan, yung mga power load requirements natin, so paano natin malalaman na ano talaga yung average, let's say average or maximum demand in the system natin, no? So ito yung nag-guide sa atin kasi listed na yung mga demand ratings ng mga equipment natin dito in terms of kVA. Okay? And identification of branch circuit assignment. So dito natin makikita paano natin ma-arrange si branch circuit natin, no? So sino yung si assignment ng branch circuit 1? Is it lighting loads? Is it convenience outlet loads? Is it ACU loads, no? Etc. etc. So ito yung the method of arranging yung branch circuits natin para it's a guide dun sa mga installers natin, no? Na ito yung si branch circuit, ito lang talaga yung loads niya, i-connect, no? So basically ganyan lang. Okay. And provide summary on the sizes and specifications. of various electrical equipment. So, mga branch circuit conductors, ano yung mga sizes nila, no? And specifications, anong type of wire. Is it going to be THN, TW? Depends on the application, no? Or where they will be installed, no? So, feeder conductors, to yung mga mas malalaking conductors na, no? Connecting branch panel boards to the sub panel boards, no? And conduits, no? Ano yung type of conduits? Is it PVC? Is it going to be EMT, REC? So what have you, no? So it provides a summary and of sizes and specifications of this equipment, and also the circuit breakers, no? And fuses. Okay. So malaking kwan talaga value si load schedule, no? In arranging our design plans, and provides a guide also, no? To everybody, all the stakeholders in a certain project, no? Be it be the project in charge, or the foreman, or even your electricians themselves, no? If they know how to read. So malaking tulong talaga si load schedule. Sabi kanina, provides identification of feeder circuit, as well as the same as with the branch circuit, no? So sabi ko na kanina, it aids electrical installers, no, in implementing the correct wiring methods and materials. So kung may load schedule tayo, proper load schedule, dun din natin malalaman kung nasunod ba yung kuan natin. Yung sa mga designers, no, na pina-specify. Doon tayo. So malalaman natin kung nag-deviate ba si installer, or pina-follow ba talaga niya yung nandun sa na-specify sa load schedule. Okay? It's a point of reference sa mga lahat ng stakeholders natin. Okay? And for the manufacturers and suppliers, no, it also gives them a guide para mas accurate yung offer nila, no? Kasi doon nakalagay na yung mga rating, sizes, types of and types of certain electrical equipment. May it be a cable, may it be a circuit breaker, no? Switches, no? So conduits. So the less na yung chances of errors, no? Pag nabigyan natin sila ng copy of our load schedule as an additional reference, aside from those yung technical specs and documents natin. So additional reference ito, kasi hindi yan makovered sa lahat na contents of the technical specifications, no? Ito talaga yung actual. So our manufacturers can use this as a validation doon sa offer nila. Okay, maraming talagang instances, no, na nagkamali yung mga manufacturers natin. So yun na, medyo sakit na sa ulo doon sa dulo, kasi yung na-deliver na equipment hindi pala match. So to prevent that from happening, we have to give them, no, the correct, no, or the most almost the correct, no, if not the most correct na schedule of loads for verification nila. Okay? So malaking tulong talaga din si load schedule doon sa manufacturer. So for you engineers, no, na yung nandun sa construction, I would advise, no, na if may project kayo, see to it, no, na mabigyan nyo ng copy si manufacturer or si yung suppliers nyo of the load schedule. In fact, also the single line diagram, if I may add, no, malaking tulong din yan for validation. Okay? So malaking kuan talaga benefit si load schedule. Kung wala si load schedule, para tayong nagtinginan sa ere kung ano yung mga kuan natin, mga requirements natin sa isang project, no? Okay. So at least now we know the importance of having a load schedule. Now for voltage drop calculations, no? So ano yung benefits na pag we do evaluation of voltage drops? So it can also aid in determining the conductor size, no? This is the second step, no, actually, in verifying the conductor size to be specified, no? If sufficient ba yung voltage level, no, at the load end, no, from one point to the other. So from the power source to the bus, main bus, then to the branch circuit panel board, then to the load itself, no? So dapat i-maintain natin yung tolerable voltage drop, kasi malaking impact yan sa mga loads and efficiency and operating characteristics ng mga loads natin, no? I will list down na natin yung mga effects natin yan dito, no? So, isang effect dyan, no, is the starting and the operation of tech equipment, especially for motor loads, no? So kung malaki talaga yung voltage drop, it could affect motor starting actually, no? And also for sensitive electronic equipment, madaling masisira yan, no? Kasi power quality issues, sensitive talaga yung mga bagong equipment natin ngayon, no? Yung especially sa mga data centers, no? Yung kaya nga may mga UPS tayong inilagay, or yung mga voltage regulators to maintain the voltage, no, if talagang nag-excess na siya. But during the design stage, pwede natin yang ma-anticipate, no, para talagang hindi na tayo mag-need later on for those voltage regulation, unless na lang talaga kung ah, yung system natin medyo kinulang na kasi marami na tayong loads, then wala tayong magawa, we have to implement no voltage regulation. But during design stage, we can do as much as we can para maiwasan na yung mga voltage drops, no? So, parang si voltage regulator, parang kuan na lang yan. It's a secondary kuan na lang, remedy. But as much as we can during design stage, dapat i-kuan na natin, i-address na natin. No? Okay. It also shows no, how well designed ba yung system natin na we have already anticipated, no? Si voltage regulators, come in lang yan kung may bago tayong or may changes tayo sa system natin, no? So, doon lang sana. But initially, kung it was properly designed from the start, hindi na sana dapat needed si voltage regulator. Okay? So, again, under voltage can result in efficient operation sa mga motor loads. So, ano yung mga byproducts niyan, mga side effects is heating, no? Kasi alam natin si motor loads is a constant power load, no? So it has to draw, uh, it has to compensate, no? Ano ba yung elements ng isang yung power natin? It's a product of voltage and current. So kung magle-less si voltage, saan niya i-compensate para ma-maintain niya yung constant power niya, para ma-operate niya yung design niya, operation niya. So doon siya kukuha, it will draw much more current na sa kanya para ma-maintain yung same power. So the effect of such, maghi-heating na yan, yung circuit na yan, then alam natin yung withstand lang ng mga motor windings natin, no? Yung mga insulation natin ng motor windings natin is is quite thin, no? Hindi katulad ng mga conductors natin na rated at 600 volts, makakapal yung mga insulation yan. But motor windings are not that as can withstand that voltage, no? So, maninipis lang talaga yung mga insulation ng motor windings natin. So, kung mag-heating yan, then eventually it will deteriorate much faster than it was designed to be, to last, no? So, yun yung impact niyan. Okay? So, a study, no, states that an under voltage of 10% below rating results in a decrease of efficiency of substantially more than 10%. So, losses na yan, no? So, dapat talaga i-address natin si voltage drop. Kaya nga, we have prescribed limits dyan sa code na kuan. So, other effects, no? Kung sa mga fluorescent light output, it will reduce by 15%. So, meaning to say, if you only need 4 fluorescent lights because of this effect, then you'll be adding more na just to maintain that same illumination, no? So, anong impact dyan? Another expense naman, then additional consumption naman, no? So, again, losses sa system. So, incandescent lights, kung meron pang gumagamit, no, mas malaki pa yung reduction by 30%, no? Sabi natin kanina, sa mga induction motors, it will run hotter and produces less torque. So, ano yung impact nan? Kung less torque na, hindi na niya kayang hatakin yung design load niya, no? So again, it's a violent cycle na it gets hotter and hotter, no? Kasi mas less torque na yung maibigay niya. So the motor will be working as much harder than it was designed to be. So mas daling masira si motor natin 'yan. So ang effect niyan, again, an under voltage of 10% sa rating niya, ang running current niya increases by 11%. So malaki na yan, no? So talagang additional heat na rin yan sa circuit niya, no? And then yeah, operating temperature is a direct proportion to the current. So increases again by 12%. So malaking factor na yan, no? Eh, ito yung mas malaki pa. Torque reduces by 19%. So ang relationship ng voltage to the torque is to the square. No? So if the voltage reduces by 10%, square mo yan, yun yung reduction ng torque. So mas malaking impact yan sa torque. No? So kung talaga, medyo malaking bagay talaga si voltage drop kung hindi natin i-address. Okay, so much for those emphasis on the importance of these issues. So uh, proceed with the actual calculation process, no? You have to address some, or we have to know some definition of terms para during the discussion mamaya, alam natin kung ano yung pinagsasalita natin ng mga terms. Okay? So, number one, very basic, is the ampacity. No? Yung term na ampacity cannot be found, I don't know ngayon kung meron na ba yan sa dictionary kay Webster, but it's our specific technical term natin yan, no? It's the current in amperes that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. No, so basically, it's the load. It's the amperes. No, the amount of amperes or current in amperes na pwede na ito yung conditions na mag-operate yung equipment natin continuously for more than 3 hours, no, hindi siya intermittent. So ito yung ibig sabihin ng continuous use, no. So may temperature rating din yung mga okay. So may temperature rating yung iba't ibang type of conductor. Yung conductors natin depende sa insulation type, no? So CTW, CTHW, tsaka CTHHN, we all know na they have their own temperature rating. So mas pinakamaliit CTW at 60 degrees, si THW at 75 degrees, at CTHHN at 90 degrees, no? So, the amount of current that they can carry na hindi siya masisira, na makahandle pa yung kuan niya, temperature handling of the insulation, ito yung tinawag natin na ampacity. Okay, so sinabi ko na kanina, si continuous load is the maximum current expected to continue for 3 hours or more, no? So, that's a continuous duty. Ito yung consideration natin, the 3 hours or more. Okay. Then, we'll be talking about later about demand factor. Ano si demand factor? So as per definition, ito yung ratio of the maximum demand of the system or a part of a system to the connected load or the total connected load of the system, no? So in equation, ito yon, maximum demand over total connected load, no? So this factor is always less than 1 kasi si total connected load will always be higher than the actual maximum demand. Meaning to say, lahat ng connected loads natin is not realistic na sasabay silang aandar almost at the same time, no? So talagang hindi yan aabot na kanya na kuan yan, mag-operate yan lahat, no? So meron lang tayong talagang tinitingnan na maximum demand, no, for certain type of occupancy, either be a residential, commercial, no, or industrial. Meron tayong mga kuan yan, meron tayong calculations process diyan mamaya, no, and meron tayong din guide sa code, no, how to assume demand factors, no, nakatabulate na yan. Okay, so ito lang talaga, magagamit ito mamaya in sizing our branch, yung feeder circuits natin para hindi masyadong ma-overkill yung pag-sizing ng circuits natin. Okay? So alam natin kung naka-oversize lahat, talagang costly yan, no? So medyo apply din natin ng engineering economics yung design natin. It's not sound na palagi tayong kuan, no? nag-oversize kahit hindi naman talaga practical. So uh, let's apply engineering solutions, no, or assumptions na para naman realistic yung or may value engineering yung design natin, no. So we have to consider also the economics. Second to safety. Okay. So another term is the diversity factor. So ibang ibang factor ito, no. If you can look at its numbers, it's like a reciprocal to the demand factor. But itong diversity factor, as per definition, is the ratio of the sum of the individual maximum demands of the various subdivisions of the system, no, to the maximum demand of the whole. So meaning to say, pag meron tayong maraming feeders, no, or may mga installations tayo na may, like for example, isang malaking industrial plant, may 3 meters yan, no, may 3 connection points to the system, but lahat is going to the same transformer, no. So ito yung diversity factor ang ginamit natin, no, in sizing up the demand of our transformer, no. If marami tayong load variations, no, may feeder tayo sa itong planta or itong klase na load. So makatulong itong si diversity factor in not oversizing our transformers, no. So yung factor nito generally varies between 1 and 2. Okay. So ang kuan dito, ang dapat nating uh, i-determine is itong si total maximum demand, no. Ito yung pag-size up ng transformers natin. So si diversity factor is between 1 and 2, meaning to say ito yung given natin, si diversity factor. Meron tayong assumptions nito. Yung number natin, yung factor natin, depends on the type of load. Is it going to be lighting load? Is it going to be power loads, ECU loads, or motor loads? No? So, medyo iba ito sa demand factor. Uh, ang gusto natin kunin dito is yung total maximum demand. Kasi ang given nito is the individual maximum demand and the diversity factor. Meaning to say, kung gusto natin makuha yung talagang realistic size ng transformer natin, ito yung gamitin nating formula. Individual maximum demand over the diversity factor. So, ang effect niyan, liliit yung transformer size natin. Kasi kung individual maximum demand, i-total natin yan, malaki talaga yan. Pero kung applyan natin yung diversity factor, i-divide natin by 1 or by 1.5 or by 2, which is ang kinuha natin, ang talagang kinumpute natin magkano yung maximum demand na para i-size up yung transformer, talagang liliit si transformer. So meron tayong example diyan mamaya paano ito i-apply, no? So meron tayong assumptions, i-apply natin, no? Depende sa type of load. So for lighting feeders, the factor is between 1 to 1.5. Si power and lighting feeders combined may be higher, 1.5 to 2. So ang kaibahan dito is given yung factor, si diversity factor, then this will be used in sizing the transformer. Kaibahan sa demand factor, no, is siya yung dapat nating hanapin, si demand factor, hindi yan given, no. Ang given doon sa demand factor is yung maximum demand and the total connected loads. So iba ito si diversity factor. This one will be used in sizing the main feeder and the transformer, no. Ito yung use ng diversity factor natin. Okay? So next term that we're going to encounter is the overcurrent. So ano si overcurrent? It's any current in excess of the rated current of the equipment of the conductor, no? Basically, it may result from overload, short circuit, or ground fault, no? So ang kaibahan lang talaga ni overload at ni short circuit is in terms of magnitude. Okay? So saan dyan ang mas malaking magnitude? So again, overload is just a slight overcurrent, no, in terms of ilang percent lang, mga 10 to 20% from the rated current, no. But si short circuit is usually 3 to 6 times, no, larger than the rated current. So mas malaking diferensya talaga from overload to short circuit or ground fault, no. So kung it's almost a multiple of the rated current, it's either a what na yan, short circuit or ground fault, no? So depends on the impedance of the system and the available fault duty. So meaning to say, pag short circuit na yan or ground fault or a fault na yan, uh, ang circuit natin is nag-deviate na, no, from the normal flow of current, no? Ang overload is normal pa rin yung flow of current from source to load back to source. It just so happen lang na lumaki lang yung current because of certain operating conditions. Like for example, yung sabi natin kanina, yung motor natin, no, kasi because severe yung voltage drop, lumaki yung current. So it might reach overload conditions, pero walang nabago sa connection, wiring connection. Ito si short circuit talagang nagbago yan ng flow of current. Kasi instead of having that complete circuit from source to load then back to source, posible na bypass si load, yung dalawang linya natin sa line 1 and line 2, nag-shorted yan or shorted to ground. So, si flow of current natin na iba na, no? Meaning to say, mas malaking current na yung dumaloy because nawala na yung impedance ng load natin, no? So Ohm's law pa rin 'yan, no? Alam natin pag yung impedance natin is lumiit for the same voltage, ano mangyayari? Si current yung lalaki. So ito yung principle talaga ng short circuit natin and other faults actually, no? So yun yung kaibahan. So but all of them, overload and short circuit and ground fault are termed as overcurrents, okay? Makaiba lang sa behavior, no? And magnitude. Okay, so before we deal with the load schedule, we have to identify or to know ano yung various parts of the system natin na dapat natin i-size up, no? So, firstly, kung design process yung tingnan natin, unahin natin talagang i-size up si branch circuit kasi dito yung nanggaling yung mga loads, no? Then from bottom up yan. So pagkatapos si branch circuit pala is if you say conductors, no, it's the conductors between the final overcurrent device, which is this one, the let's just say the lighting panel board, no. This is the last panel board. Then after this one, going to the loads na talaga. So ito yung tawag na branch circuit conductors. Okay, alam natin siguro malami natin yan na ito yung branch circuit conductors. Next is the subfeeder, no? If meron pa tayong panel board sa unahan, no, before going to the source, meron pang isang distribution panel board, then the conductors connecting the distribution panel board and the branch circuit panel board is what we call the subfeeder conductors, no? So mas malaking conductor na ito compared sa branch circuit, no, naturally. Then eventually pag nandun na tayo sa main, sa dulo na talaga, which is doon nakakonect yung main power supply natin. So the conductors connecting that main switchboard to the first distribution panel board is what we call the feeder conductors. Okay? And then, yung conductors going outside, either connected na to the service utility or to a transformer, no? Ito yung tawag na service mains. Okay? So importante yan to know them para ma-designate natin properly yung load schedule natin. Ano ba yan? Feeder ba yan? Or branch circuit ba yan? No? So, these are just terms that we need clarity lang, no? In order na mas properly arrange or properly identified yung parts of the system natin na pinag-compute or pinag-size up natin at specify natin, no? So, kung talagang nasa load na yung conductor, branch circuit. Kung panel to panel, it's subfeeder. From panel to the main switchboard is the main feeder or feeders, no? And going outside is the service mains, okay? So ito yung sa labas. So yung service entrance conductors or the service main, ito yung conductors galing sa main switchboard, no? Going to the meter and to the service entrance facility. Ito yung lalabas doon sa entrance cap natin, no? And then yung connection point ng from in our service entrance conductors and the service trap from the utility is what we call the service point, no? And then yung sa utility na, ito yung service drop conductors, no? So ito yung supplied by the utility. Okay. So the connection between these two conductors is what we call the service point. Okay? Ito si service drop conductors, hindi natin responsibility to size this one, no? Sa kay utility na yan, but they are basing that on our plans, on our electrical plans. So ano yung size ng conductors nila. And also the ampacity of this one is referred to another table, no? Yung kasing treatment nito is aerial ito na conductor. So we all know that if it's in free air, yung conductors natin can carry much more capacity than doon ng sa indoor, no? Yung enclosed na conductors. So for the same cross-sectional area, mas malaking ang capacity itong nasa free air, no? By I think almost two times. No, so wag tayong surprise bakit maliit yung service drop nyo? So we have to be reminded na it's in free air, no? So don't worry, just verify lang dun sa table natin, no? Pag talagang we are in doubt dun sa utility natin kung it was the proper size, then refer to our table. Free air yung gamitin natin na table, ha? Wag yung conductors inside a raceway na ampacity. Okay? Pointers lang, no? Okay. So again, another definition is the what we call the general purpose receptacle, no? Or usually what we call receptacles or convenience outlets. So when we say general purpose receptacle, it's those outlets na wala tagang dedicated loads, no? Na pwede plug in cord, plug-in one lang, no? Connected, no? Na walang steady na load. So mga small appliances lang pwedeng i-connect diyan, no? Di pwede yan yung mga aircon, yung mga lalaking washing machine, no? So mga dryers. Pag ganyan na mga klase na load, hindi na yan GPR sa, hindi na yan receptacles. It's a kuan na talaga dedicated outlet na, no? Yung treatment na yan. So when we say GPRs, yun yung convenience outlets na makita natin all throughout our walls na walang nakasaksak palagi na load. Okay? So another term is the equipment grounding conductor. So we all know that yung green na wire, no? So as per definition is the conductive path that provides a ground fault current path, no? So normally, kung walang fault, walang ground fault, walang kuryenteng dadaloy dyan sa wire na yan. So it's just a effective ground fault path return, no, from the faulted point back to the source para it will help in the operation of our protective devices na magtitrip siya. Kasi pag wala si equipment ground conductor, pag may ground fault ka, walang mangyayari sa circuit breaker natin. Hindi yan titrip, no? So, nandun pa rin yung ground fault, then the hazard exists kasi we all know pag nag-ground fault yan, ang effect yan is uh, tataas yung mag-overvoltage yung unfaulted phase natin, no? Depende sa capacitance or capacitive reactance ng system natin na how much it will rise up, no, yung unfaulted phase, yung line to ground voltage. So you can check that, no, pag mag-testing ka line to ground, kung three phase ka, check mo yung unfaulted phase. If may suspect ka na may ground fault ka, mas mataas yung line to ground voltage doon sa hindi na faulted na phase. Tapos yung faulted phase, almost zero yung voltage niya, or near zero or zero kung volted fault talaga. If is a arcing ground fault, then maliit yan, almost zero yan, no, or less than 100, or yung mga ganyan na values. So yan yung mangyari kung wala tayong banding. Ito yung banding na tinatawag natin. And the specific conductor na ginamit for banding, ito yung term na equipment grounding conductor. Okay? So, another term is the overcurrent protective device. Ito yung mga fuse and circuit breakers na nagbigay ng protection during overload and short circuits. Okay? So, usually, additional notes lang, yung mga circuit breakers natin, the minimum rating for the CAIC ratings for that is 5,000 amperes. Yung mga miniature circuit breakers natin, no? Industry standards, yung CAIC ratings niyan is not less than 5,000 amperes, no? Okay. So, ito yung another term is nominal or continuous current rating, no? So, ito yung rating na it can handle continuously maximum current, no? It can handle usually for more than 3 hours, no? Safely, no? So hindi yan mag-operate. So for circuit breakers, ito yung nominal rating. Makita natin yung immediately doon sa in front of the circuit breaker, in the handle or whatever, no? Ito yung mga ratings na 20 amperes, 30 amperes, 50 amperes. Yan yung nominal rating or continuous current rating, no? Kung meron tayong electronic trip units or adjustable trip unit na circuit breaker, sometimes yung nominal rating is considered also as the trip setting, no? If meron tayong adjustable trip unit na circuit breakers ng mga solid state, no? So it can be also known as the trip setting. If wala tayo dyan, then yung kuan talaga rating ng makita natin sa mga MCCB at MCBs, no? Another rating sa circuit breakers natin, by the way, yung kuan kanina is for the circuit breakers, yung nominal or continuous rating. We also have another rating ng circuit breakers natin na hindi palaging makikita natin. Ito yung si CAIC rating, no? The interrupting rating. Okay. So, bakit tinawag yung CAIC? Kasi it is termed in kiloamperes interrupting capacity. Kaya nga CAIC. So, this is the rating, no? That a circuit breaker or a fuse can interrupt safely, no, during short circuit or ground fault, no, meaning to say at those conditions, malalaking current na yan in terms of 1,000 amperes, hindi yan masisira, no, pag mag-interrupt siya. The problem now, if kung undersize yung CAIC rating mo, ang mangyayari yan pag during interruption, pwede yang ikasisira o talagang sasabog yung circuit breaker natin kung grabe yung pagka-undersize ng CAIC rating. So dapat talaga i-address. But this is not part of our topic. Ito lang, pinagkuhan ko lang ito kasi in our load schedule, isama kasi natin yan ilagay yung CAIC rating. But to arrive at the proper rating, dapat we have to conduct again short circuit calculation, no? So just an additional kuan lang inputs. Okay? So before going to the actual load schedule development, no, we have to be familiar with the installation electrical plan requirements. So bakit mandatory requirement ito, no? So as per PEC 2017 natin, it's one of the kuan, no, requirements. It's number 5, no, schedule of loads, no? So nakasabay, nakalagay talaga diyan. So hindi tayo makaiwas diyan. Requirement talaga yan in OBO submission. And additionally, lately ito yung si design analysis na hindi yan pinag-require noon, but I think last 2015 nagbigay ng memo si yung chairman mapili natin doon sa DILG, and cascading to all LGUs natin, OBO LGUs, na additional requirement na yung design analysis, no, yung calculation of voltage drops, no. So together with short circuit calculation, no. So that's why mandatory requirement itong si voltage drop during submission of our design plans. Okay, so just another one lang mga requirements for electrical installation. So dapat ang conductors natin are expressed in metric, no. Although we are ANSI, reference natin is ANSI because of NEC or the NEC na kinopya natin. But this is where the deviation starts, no? Instead of AWG yung conductors natin, dito sa PEC natin, we are specifying na express natin in mm squared yung conductors natin. Okay? And then yung permitted lang na material for conductors is either copper or aluminum, no? So yun lang, wala tayong nakitang ibang type of conductors or conductor material. And then temperature limitation. So yung kuan natin, termination for circuits, no, sa mga 100 amperes or less or mark sa wire size na 2 mm squared, no, yung conductors natin are, if unless specified, no, are rated at 60 degrees, no. So, yun yung dapat natin tandaan na usually sa mga 100 amperes or less na circuit, usually ang rating ng mga conductors natin no are expressed in 60 degrees. The default yan. Pero kung si designer mag-specify siya ng otherwise, then ma-provide naman, no? But if walang specification, usually rated yan at 60 degrees, no? From 2 mm squared to 38 mm squared na conductors, no? Okay. Then for above that one rating, above 100 amperes and larger than 38 mm squared, then conductors are usually rated at 75 degrees, no? But then again, depends talaga ni designer kasi yung iba gusto din specify 90 degrees. But again, the only point of kwan lang to be mindful of is temperature matching na kung conductors mo rated at 75 degrees, dapat si circuit breaker na gamitin mo, you have to specify also 75 degrees, no? Not 60 degrees, not 90 degrees. Para wala tayong temperature mismatch na can cause nuisance tripping, okay? So, dapat tandaan natin yan na if you want to use conductors at 75 degrees, usually yan yung mga THW na conductors, nga insulation niya. So, i-follow na lang na yung i-specify natin na circuit breaker must be 75 degrees. Especially for circuits na below 100 amperes. Kasi pag hindi natin niya specify at 75 degrees, yung usually yung mga market natin na ibibigay yung standard is 60 degrees, no? So we have to be careful on that, no, aspect. Okay? Hey, so what are the general design considerations again, no? The steps, no? Dapat nating ito yung mga boundaries dapat natin iset when we do na the actual design, no? Although the electrical design is a long and tedious process, no? But these are some of the simple steps that we can do prior to starting our design, okay? So first step begins on the basic review of all applicable provisions of the codes, laws, and regulations, no? That have jurisdiction. So ano sa atin dito sa Pilipinas? So it's the Philippine Electrical Code, PEC 2017, the latest edition, no? So yung design kuha natin, process natin, usually ang provisions makikita in chapters 1, 2, 3, and 4, no? Or articles 1, 2, 3, and 4. Yun yung kuha natin, mga talagang ginagamit natin palagi, no? Articles 1 to 4. Then other articles uh, are addressing special equipments, no? Yung other 5, 6, and 7, so on and so forth, no? For this discussion, we are focused on articles 1, 2, 3, and 4. Okay? Most of our provisions ginamit, no? So, for you to know sa ano yung mga references na ginamit natin. Okay? Then, siguro to some extent, yung RA law natin, no? Especially sections 26, 31, 32, and 34, no? So, be mindful of that lang also. And then, National Building Code can be used also as reference, no? In terms of coordinating with other trades, no? Yung separation between yung system natin with other trades, no? Okay. So, okay. And then other regulations are the what we call the DSOR, no, or the Distribution Service Open Access Rules. This concerns the electric utility connections natin, no. There are regulations that we need to follow. So that is why sometimes, or not sometimes, it's recommended na we consult with the local electric utility before we produce our design para alam natin yung mga requirements nila and ano yung system voltage nila, no? Ano yung service point connection requirements, dapat malaman natin 'yan, no? So ito yung isang kuan na that can guide us, no? Ito si Lisor. Okay. Then after doing that, then we can now start our actual design process. So we can now prepare an electrical load estimate based on area. So what we call the load density, no, method, no? Kung wala pa tayong actual loads na nakuha, no? So we have a best practice na set, no, based on square area, based on the type also of occupancy, no? For a certain type of occupancy, meron yang recommend or just we say established, no, low density per square area. No, we can do that strategy, or we can do that approach if wala pa tayong actual, especially for lighting and general purpose receptacle circuits. No, meron tayong low density approach diyan, no? Nasa code yan. But for other loads like aircon, meron tayong makuha dyan na low density din na factors, but not so much on the electrical code. As for me, sa lecture nito, I am using IEEE, no, references for those type of loads. Kung wala talaga tayo pang... Kasi ang problema sa atin sa electrical design, most often, no, tayo talagang pinakalas na matatapos. Why? Kasi tayo lahat ang recipient of the demand requirements of other trades, mechanical, electronics, no, lighting, kay architect, no. So kung hindi pa sila natapos, then tayo naghihintay lang sa kanila. So talagang maipit tayo during deadline. So to address that, we can do other strategies, no? Especially for lighting and general outlets na we have that the low density method, no? I-discuss natin yan mamaya, no? Okay. Okay, no questions so far. Okay, let's continue. Then, like I said kanina, consult the local utility company sa kanila mga requirements, ano yung system voltages nila, no? Yung connection points, okay. Then, for validation, no? After you have done your initial design assumptions based on low density, pag during the design stage na medyo yung other trades, other designers natin is medyo naka-establish na nila ng ratings ng kanila mga loads or yung power requirement nila, then we have to request for that data. Then ibangga natin doon sa assumption natin kung which of these ang mag-yield ng mas higher demand, no? So kung si low density method ang we can see na mas higher yung demand niya, then let's use that power requirement, no? Yung kay kuan, yung sa other designers, no, na ratings, we can do that na lang siguro in dong sa load assignment na, yung sa circuiting na niya, no, yung specific outlet, ito yung rating niya. But for the feeders, main feeders, we have to use which one of these is the higher value, no? Yung load density calculation ba o yung actual load ba na binigay ng other designers. But for me, as for me lang as my experience, no, I use the higher value, no? Kasi alam natin safe tayo, may allowance pa tayo, no? For just in case kung may additional loads pa sila, no? So sabi ko nga, yung actual ratings ng mga equipment na binigay ng other designers, magagamit natin yan during na lang sa dong pag-assigning na sa mga specific outlets, no? Or specific circuits na ito yung talagang rating niya sa branch circuit. But para sa feeders, I would recommend use the higher value sa yung na-compute natin sa low density. Okay? So next process is to determine the location, estimated sizes of different equipment such as electrical room. So during designing talaga, other than the load schedule, kasi gawan mo yan ng layout plan. So ito yung next mong gagawin. But di natin yan i-focus at least sa lecture natin ngayon because ito deals with layout plans na, no? Then design the lighting system. Pwede rin kung gusto mo talagang i-evaluate as per illumination level requirement. So pwede yan ikuan mo kung ilan talagang lights lang talagang required for certain area, no? Then do the circuiting of the lighting and power system. Then the single line diagram and coordinate with other trades, no? So other methods in this one is not related so much in load schedule like single line diagram, but I just give this to you so mayroon kayong idea sa design process natin, no? Overall design process. Okay? So with that being said, let's now go into the actual load schedule development process. So may process pala ito, no? It's not kasi ang usually, no, I've encountered some new engineers natin, mga designers natin. Ang nangyari talaga is parang lang pinag-copy paste lang yung ah, mga design plans ng other designers din, no? Then put in lang all the data. So we are now going into the actual talaga, no, load schedule development process natin, no? Okay. Okay, so before we do the actual uh, developing of load schedule, so ito yung steps natin, no, we need to do. Okay, first and foremost, we need to determine the load demand in KVA. So we have two approaches for that, no, like I said kanina, either in low density method or yung actual load talaga from other designers, no? Then when we have that data, we can now develop the circuit requirements, no, for lighting and outlets, no. We have already have that KVA, then alam na natin, no, how much or how many circuits do we need, no, to assign for lighting and for our convenience outlets. So that's the next step, no? Kasi ito yung mga devices na marami sa isang system, no? And they'll be spread out in various areas, no? Walang specific na assignment. So marami tayong lighting sa living room, sa dining room, etc. etc. Same also with the outlets. Kaya ito yung dapat natin iunang i-develop yung circuit requirements nila. How much circuits and uh, how much of these fixtures in a circuit, no? So meron tayong best practices niyan, no? And meron din tayong code provision limitation for outlets in a particular circuit, okay? Next, kung matapos na tayo sa lighting and outlets, then we need to assign na the circuits for specific na appliances and other power loads such as refrigerators, water pumps, no, air conditioning units, heaters, dryers, etc., etc. Yung mga lalaking loads, no. That's the third step, no. Then after doing that circuit assignment, summarize all of this in a tabulated form. Ito na yung tinawag natin na load schedule, no? So, then pag na-complete natin yung load schedule to size up now for the feeder conductors, no? We need now to determine the overall demand factor. So meron din tayong process niyan. Hindi yan parang out of the blue na factor na kasi ito rin, no, yung practices ng mga bagong kuan natin kasi because of that virtue of copy paste, no. Uh, Pinag-copy paste lang din nila yung mga previous na nakita nila mga design plans, no. Okay, wala akong against diyan kasi alam naman natin na it's a valid kuan, but is it really accurate, no? Is it really uh, near yung talagang operating characteristics of a certain facility, yung kinopya natin na demand factor. So, with that, meron tayong process din yan, how to determine the demand factor. Not, hindi lang yan random figure out of the blue, no? Okay. So, ito na. Ito yung mga details na in developing a load schedule. Okay? So, alam natin kanina, first step is to determine the load demand in kVA of various lighting loads, no? So, it can be done in two ways. Yung tawag natin kanina, low density method. So, usually applied ito in the early stages of the design where hindi pa natin alam yung quantity and actual equipment ratings, no? No? So, kaya nga we have this approach low density method na nag-assume tayo ng low density per square area based on the type also of occupancy, no? Hindi yan applicable yung low density ng isang residential, hindi yan applicable sa isang commercial at industrial facility, no? Magkaiba yan, no? So dapat we need to be careful on that, no? So we need to know ano yung type of facility ang i-design natin. Is it residential, commercial or industrial, no? The second approach will be the actual connected load calculations, no? Uh, but pag ito yung ginawa natin, more often than not, talagang matatagalan tayo matatapos sa design natin. And then alam naman natin na yung yung clients natin palaging nag-apura sa atin, no? And then paano natin ma-justify yan? More often than not, we make excuses na ito si mechanical hindi pa nagbigay, ito si ganyan. So uh, if yan yung approach natin, no? More often than not, uh, pag si client natin, he will encounter another designer na mas madaling matatapos yung design, yun na. Ayun na problema. Baka ma-compare tayo, no? Oh, bakit si engineer designer and so mas madali siyang natapos? Kasi meron siyang other approach. Hindi siya ganitong na approach lang, no? So I would recommend start with the low density. Then itong si actual load can be used now for validation na lang. During kung nandun na yung mga actual ratings, no? Or for assignment na lang of circuit assignment, no? Kung ang during comparison, makita natin mas malaki yung demand na makuha natin kay low density compared sa actual load, then we use the higher one, no? Then ito for validation na lang si actual load calculations, no, na may specific ratings na talaga. Okay? So that's for me as for my practice, no. It depends on you na kung how you do it, but as for me it works, no. Okay. So itong sabi ko kanina, use whichever method that yields the higher value of demand in kVA. Okay? Then that's where we start na developing the circuit assignment, no. Okay. So next step, pag nakuha natin yung demand in kVA, especially for lighting and outlets, no. Then we proceed with developing the circuit requirements for lighting and small power. So we need now to establish the number of required of branch circuits and the number of devices in each circuit. Okay? So ito lang, wala naman itong strict rule na how many branch circuits minimum, wala yan sa code. Really depends now sa inyo kung in terms of practicality and applicability, no? So alam natin ano yung gusto natin, reliability or cost efficiency, no? So the lesser number of branch circuits, then normally or usually mas cheaper yan in terms of installation cost. But then again, during operation, pag isang circuit lang yung lighting mo, pag nasira yung isang circuit, lahat ng ilaw ng bahay mo wala, no? So yun yung disadvantage. So you have to balance out, no, the cost effectiveness and the reliability also. So hindi yan purely cost lang. Hindi din yan purely reliability kasi mas mahal yan. So depende na yan. So you have to put in your sound engineering decision how to specify number of required branch circuits, no? Okay, so sabi ko kanina, the number of lighting and outlets per branch circuit. Okay. Then next step, pag natapos na tayo sa lighting and outlets, we go now with the specific appliances, no, yung electric range, dryers, heaters, ACUs, motor pumps, etc., etc., no? So, madali lang 'yan kasi specific 'yan unlike dun sa lighting and outlets, no? Then after that, summarize those data including their electrical parameters, no, in a tabulated form, no, in these following categories: load description, ratings, quantity, and circuit assignment. Ito na yung usually nakita natin sa yung load schedule na tabulated form na, no. So then for feeder sizing, we need now to determine the overall demand factor, no, to complete the design process, no, for sizing the main and sub feeders. Okay, as prescribed in PEC 2017. So ito yung development process talaga ng isang load schedule. Kung hindi tayo copy-paste engineer, no? Kasi si copy-paste engineer, madali lang 'yan, no? Get in all design, reflect into your design, then ano yung kuan niya, yun lang, ilagay mo lang 'yan, no? Pero yung design analysis mo wala na, no? You're just a copy-paste engineer, no? So dapat i-change natin 'yan. We have to do the design process from scratch. Ito ito yung ma-develop mo yung uniqueness mo as a design engineer kasi you are doing it your own. Siguro gawin mo lang reference yung mga previous design. Pag wag mong kopyahin outright, you have to validate, no? And you have to again, I would recommend, no, go through with this process para talagang masabi mo I have done it on my own, no? Ako talagang develop from scratch, no? So that's an achievement on your part. Okay? So, what are the basic composition of a typical schedule of loads? So, ito yung mga talagang dapat makikita, no? Kasi meron din schedule of loads na maraming data, no? Mga additional optional data. But these are talagang mga mandatory na or compulsory na data na ilagay natin sa load schedule. So, ito yon panel ID or label. Ano yung panel na description niya? Panel location, saan ba yan? Second floor, first floor, etc. etc. Circuit number description. So ano yan? Circuit number 1, number 2, 3, and 4, so on and so forth. Or and description is ano ba yan? Lighting, small power, ECU, etc. No, dapat nandyan yan. Load description, no? Oh, sabi ko na kanina. And ano yung equipment or device type? Is it a dryer? Is it a heating appliance or electric range? And then the quantity, number, no? Number of devices or equipment. Okay. And then the unit rating in power in terms of VA or kVA. So ito yung pinagbago sa kuan natin kasi previously may mga designs na ang ginamit nilang unit sa power is watts or kilowatts. So ngayon pinagkuha na talaga na dapat in terms of VA. So na-account na yan yung power factor natin yan, no? Dapat i-convert na natin kung kilowatt yung nasa nameplate, i-convert mo na to VA or kVA para standardize na yung units natin sa load schedule, no? Okay. The next is the parameters, the system voltage. Is it ano ba yan? 400, 480, 230, etc. etc. No? And anong number of phase? Is it single phase or three phase? Dalawa lang naman yan. Wala naman tayong ibang phase system, no? So, is it either single phase or three phase? And then total kVA load per circuit or per each branch circuit, no? Dapat ilagay natin. Then total current amps per circuit. Next is the device ratings, protective device ratings. Is it going to be a fuse or circuit breaker? So dapat nakalagay yan yung ampere trip, ampere frame, number of poles, no? So sometimes si ampere frame pwedeng wala, dapat na si ampere trip, but mas mabuti maglagyan mo si ampere frame kasi ang value diyan is ito, it will give the manufacturers or suppliers an idea kung anong direction ni designer na is he anticipating an expansion later on, no? Kasi ang value ni ampere frame is if you have circuit breakers na within the range dun sa ampere frame niya kasi yung ampere frame is ranges of the sizes of circuit breakers yan, physical size, no? So usually yung mga 20 ampere, 15 to 50 ampere na circuit breakers, yung ampere frame nila is sa 50 amperes lang yan, no? Limit, maximum. Meaning to say, kung gusto mong mag-upgrade from 20 amperes to 50 amperes, hindi mo na problemahin yung kung mag-fit in ba yung circuit breaker mo kasi they are on the same ampere frame. So convenient yan sa atin, sa mga installers, no? Na kung gusto mong palakihin kasi may additional loads ka, so hindi mo na kuan pa yung paano natin i-fit in yung circuit breaker, mag-retrofit ba tayo sa panel board, hindi na, basta within lang sa same ampere frame yung breakers natin, no? So yan yung kahalagahan ng ampere frame, no? Usually kung designers nag-specify ng ampere frame, they have already anticipated that in this particular portion of the system posible itong mag-expansion or mag-add na mga loads. Kaya nga pinag-specify niya na anong ampere frame gusto niya, up to what ampere frame yung kuan natin, no? So para convenient during mag additional loads tayo later on. Okay? Then next, compulsory composition is the branch and further circuit conductors. Naturally, yung conductors natin, anong type and anong size, no? So, ah, kasama na yan, ilagay natin yung line conductors and neutral conductors kung meron in a three-phase five-wire system, no? Na may neutral loads, dapat ilagay natin yung type and size of conductors natin, no? And also the equipment ground conductor, no? Lagay natin yan sa load schedule. And then the conduit specifications, yung type and size, okay? So ano yan, PVC, EMT, REC, and the diameter sizes, no? No? So next, meron tayong optional data, no? Pwedeng wala, pwedeng lagyan nyo ito for additional information, no? For more clarity. So, pwede natin lagyan anong type of panel enclosure. So, helpful ito sa mga panel suppliers natin para makita nila agad, no? Ano yung gusto natin sa particular panel board na ito. Ano ba yan? NEMA 1, NEMA 3R, NEMA 4X, etc. So, pwede natin lagyan yan, no? And ano yung load connection or configuration? Is it going to be Y connected loads or line to line? So, ang usefulness nito is kung may mag-review dun sa design natin, no? They can be made aware na yung system natin is a line to neutral loads or line to line loads, no? So, yun yung kahalagahan nito, no? They can give it a much more clarity kung anong yung type of system natin. And then, additional optional data is the bus bar KA withstand bracing. Ang value nito is for manufacturers again na dapat yung mga bracing nila sa mga bus bars nila are rated for certain kiloamps na fault, no? Para it can be assured na during faults or during short circuits, hindi yan properly brace yung mga bus bars natin, hindi yan masisira, no? Kasi malaking force yan yung kuan natin, yung short circuit natin, mechanical force yan eh, no? Magnetic forces na at play during short circuits, no? So dapat they have to be braced properly na hindi yan masisira. So it can give an additional data na although alam naman natin na sa Pilipinas seldom lang talaga yung panel manufacturers natin na type tested yung mga panel boards nila, but then again okay lang din naman na at least at your end as a designer, you are also conscious about giving this information. Malay natin uh, kung yung manufacturer na kinuha natin is uh, can have the ability, no, to really determine ano yung pag-brace sa ganitong klaseng fault. So at least binigay na natin yung data, no, kaysa wala. Okay. And then optional also is wire color coding. So it's going to be RYB, etc., etc. So siguro sa mga cable suppliers natin, it can give them an idea kung yung load schedule natin, yung system natin, nag-specify ba tayo ng color coding, no? Okay, so this is a typical entry of a load schedule, no? So lahat yung sinasabi natin kanina, nandito yan, makikita natin, no? Meron pa tayong project name and address. So optional yan. But you can skim through this one, no? Alam naman natin, a lot of you are also familiar with this one. So this is just some of my suggestions, no? Additional data, if you may, no? Na pwede nyo magagamit. So ibigay ko naman ito. So it's for your consumption kung i-adapt nyo ito or you do your own, no? Or you can improve from this, okay? So again, we have to start with yung referencing natin, no? As per PEC 2017, yung design, consideration, and references, paano pag-sizing ng conductor before we go with the actual calculation. Madali lang yung calculation but we need to know saan natin kinuha yung mga reference natin. Bakit ganyan ang yung pag-size up ng branch circuit at feeders, no? So, pinag-summarize ko na dito, no? In fact, I've also already also provided which article can you find this kuan design consideration para you yourself you do your own validation. You you search in our code book, no, kung hindi ba ako nagkamali, no? So you have to validate yourself. Huwag kayong mag-rely lang dito sa slides ko because it might be sometimes, no, may na-miss out ako o may nag-error ako. then it's your kuana, it's your due diligence, no, to do your validation. That's why I put in here the provisions para ma-check nyo rin, no, kung accurate ba yung nailagay ko dito na provisions. Okay? So for sizing of branch circuit conductors, so these are the conductors again between the final overcurrent device, or shall we say the branch circuit panel board of a certain device, either lighting or outlets or other loads, no, to the equipment itself, no. Pinaka-last talaga ito. And also the same with the branch circuit overcurrent protected device. Just a little review lang, no. So let's start with the uh, lighting loads, no, demand, no. So first, yung sinabi natin load density, no. So kasi let's assume wala pa talagang naibigay si architect na number of lights and the wattage of those, or the illumination, no, required, no. We can start with the illumination calculation, but for this one, meron tayong tabulated, no, na low density for certain occupancy, no. So meron tayo sa article 2.20.2.3, no, table 2.20 for the same article, no, for specified occupancies meron tayong tabulated yan na low density required, no. So again, reminders lang, each floor area shall be calculated from the outside dimensions, no. Kung may layout tayo, dapat yung area is measured, no, outside dimensions, not the inside dimensions of the building, no. Ito yun lang yung dapat natin pagtutunin ng pansin, no. Not the inside but the outside dimensions of the building. Okay? So ito yung table na minention kanina for certain type of occupancy, no. So for example, no, dwelling units, no, this is the most common. So we have a unit load of 24 volt amperes per square meter, no. So basically, kung may bahay ka na, let's just say 100 square meters, so times 24 volt amperes per square meter, so that's 2.4 kVA na, no? Tama ba? 100 tama nga. So you have a load or demand na established load of 2.4 kVA for lighting circuits. Diyan lang kasimple yung pag-establish ng load density for lighting. Kung ibang occupancy yan, then use the appropriate figures, no, accordingly, no. So ito yung table guide natin, okay? So may exemptions lang, hindi included, no. Excluded yung mga open porches like this one. I don't know if we have houses like this one, but usually in US they have this open porch. Meron siguro yung mga malulumang bahay natin, no, yung mga pre-war era, meron mga open porch, so hindi yan kasama sa low density area, occupied area, or even garage. And yung mga unfinished spaces, no, na hindi siya pwedeng i-adapt for future use, no. So kasi maliit lang yung area niya, and then wala talagang magagamit yan for conversion for use in the future. So it depends na lang sa inyo kung how to determine that. Okay? Basta excluded yan, no, sa load density calculation ng area. Okay. So for other load demand like banks, all other occupancies, no. Okay. Ito yung provision, no. So other loads demand, other occupancies. So for outlets, okay, for other load demands, for each outlet for general use receptacles or GPRs, or not used for general emission, should be not less than that calculated in these articles 2.20.5 through L. So meron tayong mga conditions niyan. Dapat ito yung other loads na hindi dwelling units, no. So item A, kung specific appliance or loads, ang consideration niyan, no, is the ampere rating of the appliance or load served. Ito na yung sinabi ko kanina na hindi na natin ma-applyan talaga ng low density, no. So ito yung limitations. So dapat we have to have an idea no? Na paano 'yan, no? That shall be research for in the market. Ano yung mga typical ratings ng ganitong klase mga loads, no? Asa man ka? Meeting sa ta. Yeah. So, but uh, meron akong ibigay mamaya, no? Especially for aircon loads na IEEE yan na reference kasi ito wala ito sa code, no? So meron akong ibigay mamaya for power loads for recommended sa IEEE load density rin na values, no? So you can also use that but as per code wala siyang binigay sa atin, no? So ito yung binigay niya ampere rating of the appliance or load to be served. This is for specific appliance hindi na yung sa mga general purpose receptacles. Okay. So same as for uh, meron tayong considerations din yan, no? As per 2.20.13.15. Okay. So for clothes dryers, mayroong binigay si PEC na minimum watts, no? Or in volt amperes, it's 5,000 watts or 5 VA. But then again, we have to validate this one. Either that or the nameplate rating, whichever is higher, no? So, if you care to research again, ano yung volume of dryer na talagang needed ni client natin. So, we have to do our own due diligence to research, no, the nameplate rating talaga. But in the absence of such, pwede nating we start with the 5 kVA rating, no? But then we have to validate it later on, no? Okay. Motor outlets, so ibang treatment din 'yan. It's in Article 4.30.2.2 and I've already put in here para as reference niyo. So, si single motor loads, ibang approach. Several motor loads, meron tayong calculation for that. But we need the we have spare discussion for this one later on, no? So, ito lang yung mga code provisions na inilagay ko muna dito, okay? For luminaires, no? Uh, shall be calculated based on the maximum volt ampere rating of the equipment and lamps of which the luminaire is rated. Ito yung one consideration for non-dwelling units yung tawag natin na other occupancies, no? So, but then again, pwede naman natin i-compare. For me, kung hindi lang yung mga heavy duty lamp holders, no? Pwede natin gamit yung low density talaga, no? Ito for validation na lang ito later on, no? Yung actual rating of the luminaires, no? Okay. So again, additional notes, no? Where the rating of the luminaires installed for general lighting exceeds the minimum load provided in table, yung load density natin, then uh, ang i-adjust natin yung assumption natin na ang gamitin natin na KVA, VA rating talaga is yung sa actual installed luminaires. If in case no lalagpas yung actual no connected load versus doon sa load density na ginawa natin. Yun lang yung dapat natin pagkabantayan, no? Kung lalagpas na siya. Okay? So in general, no additional calculation is required for luminaires, either recessed or surface mount, installed in dwelling unit because the load of such luminaire is covered sa 24 VA. Yun yung sinabi ko kanina, no? For dwelling units, wala talagang kuan. But for other occupancies, we need to validate talaga, no? Malaki na kasi itong 24 volt amperes per square meter, no? And minimum, no? Na rating is 600 volt amperes. Ito yung mga malalaking lamp holders natin, no? Heavy duty. So, a minimum talaga. But then again, if yung actual is much higher, then use the actual, no? I-validate natin during actual loads. No? Sign and outlet lighting, meron ang required minimum of 1,200 volt amperes for each branch circuit. Ito yung mga signage natin, no? Sa mga stores natin. So, may pinaspecify talaga si PEC na minimum of 1,200 volt amperes na branch circuit. Okay? We have to be mindful of that. Kasi minsan nakaligtaan ito eh. Okay. So, ito yung branch circuit requirements, dapat yung sa signage outlet, no, one outlet in accessible location for each tenant, no. So dapat yung signage out ko niya provide talaga is at least one, no. If hindi kasya yung one, then put another outlet, no, for signage outlet, no. And then it has to be supplied by a branch circuit rated at least 20 amperes. So alam na natin yan, ha, hindi 15 amperes but 20 amperes yung mga signage branch circuit natin. Okay? And supplying no other loads. Yun yung kuan, wag mong haluin ng ibang loads. Okay? So sabi ko kanina, minimum of 1,200 VA, or kung actual load mas malaki, then use the actual load, no? Whichever is higher talaga. Show window, meron din itong requirement, no? Uh, so dapat may unit load per outlet, no? And then ang treatment natin na demand niya is 200 VA per linear foot, no? Or in metric is to 300 mm, no? Sa show window 'yan. So if you have a 12 foot show window, multiply that by 200 VA, 'yon yung total demand required niya, okay? So ito yung unit consideration niya, 200 VA per linear foot. Okay. Okay, ito yung tinawag ko kanina, no? Kung 10 feet 'yan, then times 10. 200 times 10. So 2 kVA yung kuan mo. 'Yun lang. Okay? Ito, next consideration sa mga fixed multi-outlet assemblies, usually sa mga manufacturing firms, no, may mga multi-outlet assemblies na naka-fix like this one, no. So ang consideration niyan is kung ang use niya is non-simultaneous, no. So ang conservative specify ni PEC, no, is that each 1,500 mm, so meaning to say each 1.5 meters pala, the whole of that is rated at 180 volt amperes, no. So para siyang isang outlet, consider siyang isang outlet yung the whole, even though you have 5 outlets, but then again kasi hindi magkasabay ang consideration niya non-simultaneous use, so you can assume 180 volts amperes yung demand niya for the whole assembly, even though 5 outlets yan, but 180 volt amperes pa rin yung consideration mo, no. But if it's considered as simultaneous use, makasabay lahat, then each 300 mm, no, of kung naka-arrange yan for each distance between outlet is 1 foot, no. So in the next foot is may outlet ka na. So ang consideration niya, each 300 mm is rated at 180 volt amperes, no. So meaning to say, no, so kung may 1,500 mm ka, no, so ikuan mo yan, divide mo yan, 1,500 times 180 divided by 300 mm, no. So the total demand mo yan is 900 VA, mas malaki na compared doon sa 180 volt ampere kasi magkasabay na yung gamit niya. So ito lang yung pagtutunan natin, ha, na each 300 mm na yung treatment niya 180 volt amperes, no, not the whole 1.5. So mas conservative na ito. Okay, this is for fixed multi-outlet assemblies. First mic, may anong oras po tayong kuan, yung allotted natin dito po?
3 hours naman po,
3
sir.
hours. Okay, so up to 4 o'clock, no?
Ito.
Okay, so para makuha ko lang yung pacing ng delivery. Okay, thank you po, Press. Sige, siguro by 3 o'clock, can we do a 5-minute break lang muna, no? Bathroom break. Kasi medyo mataas pa rin
Sige po.
yung kuan. Okay, thank you po. Okay. Sige, so for meron tayong dapat din mga malaman na limitations, no, for convenience outlet or yung mga GPRs natin, no. So for banks and office building, ito yung dapat natin ikuan na, no, na each outlet, no, should not be less than 180 volt amperes. Yun yung demand na for a receptacle having or for one yoke, no. So ang declare natin na kuan is 180 VA per outlet, no? But kung mayroon na tayong dalawang gang, no, like for this one, 180 volt amperes pa rin yung treatment na demand niya. So meaning to say, pinag-consider niya na hindi magkasabay itong magagamit, no? Even though dalawa sila, no? Most of the time, ha, most of the time. Up to 3 receptacle per yoke, yung treatment natin for the demand is still at 150 VA, no? Parang isang outlet pa rin siya, no? Kahit tatlo siyang receptacles, no? But it will change kung apat na yung yoke niya, yung receptacle niya per yoke, no? So okay, so yung kuan niya, per receptacle na ngayon is treated as 90 VA per receptacle. So kung may apat ka times 4, kaya nga yung isang outlet na ito is rated at 360 VA. So hindi na 180. So parang consider niya na parang dalawang outlet will be used almost at the same time, no? So ito yung dapat natin pagbantayan na pag-apat na ito in one yoke, it's already a 360 VA demand, no? Yung outlet na ito, particular outlet na ito. Okay? So yun lang. Yun lang kaibahan, no? Sa up to 3 receptacles 180 VA, but pag-apat na 360 VA na yung demand niya. Okay? And then for limitation for in the branch circuit, no? Again, meron tayong limitation sa 15 amperes dapat hanggang 10 outlet lang siya, no? Hanggang 10 outlet lang siya, no? Ang limit niya, no? It may be a combination of a 1 gang, 2 gang or 3 gang, no? Or 1 receptacle to receptacle per outlet, okay? Then for 20 amperes hanggang 13 outlets lang, no? Yan talagang ang permitted talaga sa code natin, no? So hindi yan only, ha, kahit pa nagkuhan. So dapat followin natin yung minimum prescription ng code natin, no? Hanggang 13 outlets lang. Okay? Yung 20 ampere. Okay. Okay, so for dwelling occupancies na sizing of branch circuit, no? Okay, so um ito, no? Sa may yung outlets natin for dwelling occupancies, no? Especially specified in articles J1 and J2 and J3, can be included in the general lighting load calculation. So medyo hindi higpit dito sa dwelling units, no, natin. Yung mga outlets natin pwede nating isabay, no, sa general lighting circuits. But for me, for best practice, pinaghiwalay ko talaga si outlet, no, para kung may problema si lighting circuit, hindi madadamay si outlet and vice versa, no? So we have a certain amount of reliability na pinuput in natin sa system, no? Pero yun nga, ang trade-off doon is the cost. So kasi yung code natin uh, is not a design standard for best practice. It's just for safety, no? So for this one, ang treatment ni code nito safe naman i-combine yung convenience outlet at si lighting load in a dwelling occupancy, so no problem. Hindi niya saklaw na yung paano kung pasisira si ganyan at si ganito, so wala na yan sa code, no? But it's already on your part na, no, na kuan yung best practice na ano ba to, kung practical ba ito na isabay ko, pag nasira ito then damay lahat, no? So isa inyo na yan. Okay, so may question tayo, no, by Jason Narito. How about sa mga office load, example desktop laptop, still maximum CO is 13 sets for, yes, walang kuan po, walang exemptions, no, yung limit ng CO natin. So ang nangyari kasi kadalasan, hindi na ito na follow, kaya nga parang regular na yung parang kahit ilang sets, outlets na lang, no? So dapat follow pa rin, sir, yung kasi yung si computers natin na parang tinitreat na natin din na kuan yung GPRs. But if you want to have a standard, then but it still follows, no? It still follows na kuan na kasi para siyang i-combine loads pa rin yung mga computers natin, no? So follow pa rin tayo sa limitations. Okay, thank you for that question, no? So moving on. Okay. So, pwede, yung itong mga following outlets na pwedeng isabay sa generating load calculations, ito yung mga GPRs for 20 ampere or less na mga circuits, no, including outlets na connected sa circuits in bathrooms and also in outdoor outlets, basement, garage, and accessories. But again, hindi ito saklaw sa lecture ko, but for these areas, ang mga outlets nito dapat naka GFCI na and then naka weatherproof, so mga outdoor outlets. So additional ko lang yan for safety, no? If mag-specify na tayo ng outlet, okay? In guest rooms, no? Banks and office buildings, okay. So sa mga outlets ng office buildings, no? The calculated load from 2.2.20 point I kanina, pwede yun yung gamitin natin assumption, or the low density of 11 volt ampere per square meters, no? Ito yung for banks and office buildings, okay? Whichever is higher again, no? Whichever is higher again. Okay. Then all other outlets na hindi na covered dung from A to K, all other kwan is treatment natin is 180 volt amperes per outlet, no? So review lang yung A to K, then if does not belong to those specific considerations, then it should be based on 180 volt amperes yung demand niya per outlet, okay? Demand ito ha, demand. Okay. Okay, so for sizing of the conductors na, no, kanina yun yung mga demand natin, no, ang assumptions. Ito for sizing na talaga for conductors and circuit protection, no. So as per PEC 2017 article 2.10.2.2, please look into this one also para masanay kayong mag-open ng PEC natin. Ito yung exercise natin, no. So every time may ilagay si particular resource speaker na mga articles, no, especially in PEC, uh, do your own initiative, no, na look through that particular section, no, para masanay din kayo mag-open ng PEC natin, no, especially those na gusto mag-take ng PEE, then start exercising, opening your PEC books, no. Okay, okay. Follow-up question kay Jeffrey, no, sir, sa isang branch circuit, per gang po ba or kung ilang outlet? Ito, outlet yan, yung branch circuit po, 13 outlets. So kahit anong ilang gang yan per outlet, basta ang limit yan is doon sa 15 amperes is 11 and 10 pala, then 13 doon sa 20 amperes, kahit ilang gang po yon. Okay, thank you po. So ito yung pag-sizing, no, minimum allowable capacity, meaning to say pwede natin itong palakihan, no, wag lang pas mababa ito sa pinag-prescribe ng code. Okay? So ito yung permitted niya, not less than the non-continuous load plus 125% of the continuous load. By the way, before we proceed, no, I think I said kanina, natapos ko na yung previous considerations. So before we proceed with this sizing of branch conductors, can we have a 5-minute break, bathroom break, press? Okay lang?
Yes, sir. No problem po.
Okay. Thank you po. I'll be back in 5 minutes. Okay. Thank you, thank you. So, bathroom break tayo muna, no? And coffee break. Tamang-tama.
Gov? Gov? Excuse po, Gov? Hello? May mga questions lang po tayo dito, Gov.
Okay, sorry po. Medyo intermittent, no? Yung internet kanina. Thank you, Press. Thank you, Press. Okay. So let's proceed. Yeah. Okay, so may questions tayo.
May questions lang po, Gov,
Let's
na
address this lang
nakita ko.
muna before we proceed, no? Okay. Okay, yes, I'll be giving my copies, no? For this one. So, sige, yung may discussion tayo, no? Regarding this one, no? We'll answer this one later. Okay. Sir, ask ko lang sa PEC kasi ay 1.5 VA per circuit and 180 volt ampere outlet. Therefore, the number of outlets per circuit is at least tama po ba, sir? Yes, ito yung ang recommendation pero allowed tayo po yung up to 10 outlets nung sa 15 ampere circuit, no? And then sa 20 ampere is up to 13. Maximum na yan, no? Okay. The rating factor ng cable temperature, voltage, and ampere, hindi ba, sir, consider sa voltage calculation and load schedule? Yung yung the rating, ang voltage shop kasi, ang component lang yan is yung impedances ng cables natin, no? So ano yung size of cable na initially na size up natin, kasama na yung derating factor. So ang kino-consider lang ni voltage drop is yung impedances. So yung derating factor doon yung sa load calculation natin, sir. So ano yung resulting size ng conductor natin during load calculation with apply derating factor, mo follow lang yun si voltage drop. So ano yung impedances ng cable natin. Okay, so let's proceed. Ay, okay. Parang ito na, no? So let's go now with the sizing of branch circuit conductors and its circuit protection, no? So as per this article 2.10.2.2, so the minimum allowable ampacity of our conductors or our circuit should be not less than the non-continuous load plus 125% of the continuous load. So alam na natin kanina ano yung si continuous load, no? So those are equipment operating at more than or 3 hours or more, no? So meaning to say other loads na hindi nag-operate ng ganyan na conditions are considered non-continuous. So hindi na tayo mag-multiply pa ng factor of 125%. So mean to say pwede nating 100% siya yung duty niya, no? So yung 125% is an allowance, no? Kasi ang kuha natin is we should not load our circuits beyond 80% of its rating para talagang ma-address yung issues about temperature, no? So even though rated siya for 20 amperes but recommended or permitted lang ng code natin is just load. No, si non-continuous pwede yan 100%. So kung ano 20 amperes pwede nating isagad yan si non-continuous kasi hindi siya nag-operate. So meaning to say not as much heating as that compared to those continuous load. So permitted tayo dyan. So dapat kung continuous load siya, like ano ba yung example ng continuous load? Operating for more than 3 hours. Normally lighting loads, no? Considered yan as continuous load, no? So yung ibang loads medyo intermittent yung duty, no? Si aircon loads may thermostat yan, so para intermittent duty din yan. So pwede yan mag-on off for certain periods of time, no? So itong si lighting usually talaga yung operating for more than 3 hours, no? So usually ito yung pinag-multiply natin ng 125%. Okay? So that's for conductor sizes. Then for overcurrent protection, straightforward lang. So ano yung rating ng computation natin for the conductors, i-match na lang natin si breaker, no? And then so may question tayo diyan later, no? Na sir, kung hindi uh, wala yung computed load natin is walang industry standard na rating. So anong gawin natin? Upsize or downsize? So meron tayong consideration yan mamaya, okay? So just to give you an advance lang ako na i-discuss natin mamaya ano yung treatment natin for that case, okay? So but basically ito yung consideration natin. So for lighting and outlet circuits, ang circuit protection niya or current protection niya pwede na natin i-match kasi same one lang, same equation pa rin yung ginamit. Okay? So, para sa akin, for best practice, pinag-match ko na lang yung ampacity ng conductor with that of the circuit breaker natin, no? Okay, okay, ito na. So, when to use the next higher OCPD rating? Just in case na walang standard na mafi-fit, no? Na mag-match doon sa kuha natin. So, these are the considerations when to use the next higher standard. So, hindi ito ko mayroon tayong mga conditions dito that has to be met para we can use the next higher standard rating. Okay. The kasi advantage of the next higher standard rating is hindi ito susceptible to noise and stripping, no? But then again, we have to be careful kasi may tendency yan na hindi ma-protected yung circuit natin kasi hindi nag-match, no? So that is why ito yung mga conditions. So the conductors being protected are not part of a branch circuit supplying more than one receptacle. Okay. So meaning to say, hindi ito pwede sa mga general receptacle outlets, yung mga cord and plug connected portable loads, no? Kasi kung more than one yan in a circuit, wala na yan. Hindi na yan included. So usually ang ginamit to sa mga dedicated loads, no, isang load lang, yung isang outlet sa isang circuit, like for example refrigerator, mga ganyan na klaseng load, walang isa lang siya talaga sa isang circuit, no, even motor loads, no. So yung mga iba multi outlet na circuits, wala na yan. Hindi na yan pwedeng gamitin yung next higher standard rating, okay? Kung mag next higher standard rating ka, dapat ihabol mo yung size ng conductor mo. You cannot use the same size na compute mo with that provision and then maintain mo yan tapos mag next higher ka kasi gusto mong walang tripping. Kung hindi mo na meet yung condition, then dapat ihabol mo yung size ng conductor with the rating of the circuit breaker. Yun yung implication yan. Okay? Next condition para pwede tayong makagamit ng next higher is the ampacity of the conductors is not corresponding with the standard ampere rating of use circuit breaker. Pero kung meron siyang adjustable trip unit, the overload trip adjustment of that particular circuit breaker, no? So, meaning to say, dapat talaga i-match mo rin yung trip setting kung meron man siyang adjustable trip unit. If wala, then you cannot use the next higher standard rating. Again, kung tingin mo mag-cause ng noise and stripping yan, kung i-upsize mo yung the next higher standard rating yung gusto mong gamitin, dapat ihabol mo yung size ng conductor mo. No, no way around yan. Ha? Maintain yung conductor size, then select a circuit breaker na merong adjustable trip unit para ma-adjust mo yung overload trip na mag-match dun sa ampacity ng conductor. Ito yung ibig sabihin nito. Okay? And the next condition, pag up to 800 amperes lang yung pwedeng gamitin yung the next higher standard rating. No? For circuits beyond 800 amperes, kung wala kang adjustable trip unit, dapat ima-match mo na yung conductor. So, for example, if ang computed mo, ang capacity ng conductors mo is nasa 850 amperes na, no? Okay. Beyond na yan sa 800 amperes. So, anong choices mo? So, next size yan is 1,000 amperes na. Malaki na, no? So, okay ba? Or hindi? So, hindi. Kasi beyond 800 amperes na. So, you need to select the next lower size. But if in case it will cause noise and stripping, So hindi yan practical. If you're going to use the next higher standard 1,000 amperes, then make sure yung ampacity ng conductors mo ay magmamatch din sa 1,000 amperes. Either you upsize your conductor or you parallel conductors na yung resultant ampacity niya is yung 1,000 amperes. Okay?
Third question.
Okay, so British standard specifies that yes po. Yes sir, go ahead.
Sir, may mga circumstances na i-apply din ba yung next lower? Paano sir yun? Ganong pagkakataon.
Yung kuan nga, if ever po hindi mag-match yung kuan mo, like kanina, sinabi ko kanina, no, na ang 850 amperes yung capacity, computed mo capacity ng conductors mo. So, kasi beyond 800 amperes na ito, so dapat next lower standard rating yung gamitin mo if gusto mong i-maintain yung capacity ng conductors mo. Hindi mo na pwedeng magamit ng 1,000 amperes yung next higher. Kasi malaking discrepancy na yan, yung protection capability ng circuit breaker mo versus doon sa ampacity. So parang kung may overload, pwede na yan masisira yung kable mo kung the next higher standard rating yung gamitin mo. So dapat the next lower standard rating, if hindi siya mag-cause ng noise and stripping, then okay na yan. No? If mag-cause ng noise and sleeping, then no choice ka, mag-upsize ka. But then again, consider also matching yung capacity ng conductor mo dun sa trip setting ng circuit breaker mo, sir. Yun yung implication yan. No?
Okay, sir. So, kung wala sir sa table ng breaker, sa kung sir mag-a-adjust sa cable. Or
Yes, sa
yung
cable.
cable sa breaker naman. Okay, sir.
Yes, or you can employ adjustable trip units, sir. Whichever is cost efficient, no? Of those options. I-research mo lang muna before ka mag final selection. Magkuhan yung mga adjustable trip unit, no, just to save on cost sa cable. So dan doon na papasok yung engineering decision mo. Alam mo na yung mga strategies. So i-kuhan mo lang, i-evaluate mo lang yung effectiveness ng options mo. Okay? Sige, thank you for the question, sir.
Thank you rin, sir.
Okay, let's proceed, no? So there are some examples like this one, no? For example, you have a number 6 American wire gauge for continuous load of 44 amperes, no, times 1.25. So you'll be having a 55 amperes, no? So yung circuit breaker mo is the next size higher is 60 amperes. Okay. So meaning to say as long as yung kuan mo, ang load mo is single load lang, not part of a multiple outlet. Ito yung one of the conditions na permitted tayo to allow the next higher standard rating as long as it's up to 800 amperes, no? Ito lang yung conditions niya, okay? So ito yung mga examples na allowed tayo, no? As long as isang load lang siya. Okay? Ang wisdom kasi niyan is ito, no? Yung isang load kasi in a single outlet, predetermine na natin yung load amps niya na hindi siya aabot talaga doon beyond sa capacity ng circuit breaker natin or yung wire natin. So meaning to say, hindi talaga siya makakause ng overload. So yung protection natin doon sa circuit breaker, more often than not, it will provide na lang yung short circuit at ground fault protection na ng load natin. Right? Just like in motor circuits, no? But if it's a part of a multiple outlet, hindi natin alam na yung ibang outlets, no, mag-add yan ng current sa yung conductors mo, hindi na predetermine yung current natin. So it may chances na makakos na yan ng overloading ng circuit natin. So kaya nga hindi allowed yung mga multiple outlets na the next higher standard rating yung circuit breaker natin. Yun yung wisdom niyan. Bakit ina-allow siya? But in other cases, kung talagang afford lang, I would rather match na lang yung kuan as much as we can, no? Mas safe kasi yan. Ito kasi yung code permitted tayo because there's a certain wisdom there, no? Pinagkuhan din nila yung cost efficiency na safe pa rin. But then again, for your peace of mind, para sa akin, why not match na lang yung conductor tsaka yung circuit breaker natin, no? Yun lang yung po, yung i-suggest ko. Okay? Now, for air conditioning loads, which we usually consider as hermetic refrigerant motor compressors or hermetically sealed, no, na loads, ito yung as per PEC Article 4.4. So ibang article na ito ha, hindi na to 2.2. Yung 2.2 is for the yung other appliances yan na circuits, no, lighting, outlets, and other non-motor loads. But for motor loads, ibang article na sa PEC natin is for Article 4 na ang nag-deal dyan. Okay, so care to skim this section, no, para at least mapamilyar kayo. And then you can validate also my slides. Okay, so as per this article, yung conductors natin should have an capacity not less than, again, 125% of either the motor compressor rated load current or the branch circuit selection current, whichever is greater. Okay, so as per practice, sa akin, usually yung branch circuit selection current na doon sa PEC natin, usually higher siya, no, than the nameplate motor load. So kaya nga sa akin automatically ginamit ko na yung table kasi siya yung much greater than the two currents. So yung tawag natin na FLC, full load current, no. Itong sa nameplate, ito yung term natin na full load amperes, FLA. Yan yung ginamit na distinction ng terms, but same current pa rin yan, but magkaiba kasi yung may slight difference kasi sa value or sa magnitude. So much higher si branch selection current or what we term as FLC. So kaya nga yung table ng PEC, ito yung ginagamit ko for the selection of motor circuit conductors, hindi si nameplate. Si nameplate ginamit ko for sizing the overload protection lang, no? Not the circuit breaker. Kasi for motor circuits, iba na yung function ni circuit breaker. Si circuit breaker now functions as a short circuit and ground fault protection, not for overload protection ng motors. Ang overload protection ng motors is handled by the overload relay na, either solid state or yung thermal overload relays, no? Kaya nga ibang settings yung overload relay doon sa circuit breaker. Okay? So kaya nga yung iba gumamit ng motor circuit breaker na walang inverse, no? Walang thermal element. Instantaneous lang, tapos especially for fire pumps, no? Para hindi na magka-problema sa coordination, no? Kasi ang problema ng motor during starting eh. So dapat i-coordinate mo yung circuit breaker mo dun sa starting requirement ng motor na hindi siya mag-trip during starting. Yun yung especially for bigger motors, no? Okay. Yeah, tama po, Sir Regidor, no? FLC is from the PEC table. Okay? So with that being said, let's proceed. So again, 125% of the motor, either FLC, no? Or yung whichever is greater, okay? Then for the circuit breaker or fuse, okay? Ito yung multiplying factor niya, it's 175%. Minimum ito, no? 175% shall be permitted, no? But in case na magkukos siya ng noise and stripping during starting, it can be adjusted up to as high as 20 to 25%. Ito lang permitted natin, no? Kasi beyond this, the circuit breaker may not be able to protect now our circuit from short circuit and ground fault. Ito yung implication yan. Kaya nga hindi tayo dapat lalagpas ng 225% yung multiplying factor natin. So as low as 175 and as high as 225%. Okay? Yun lang dapat tandaan natin ha for air conditioning loads, no? Yung hermetically refrigerant motor compressor na type of loads or aircon loads for that matter. Okay. So for motor loads, ito yung sizing natin. So at section 4.30.2.2, so care to look into that one. So again, for conductors for motor loads, ito yung mga non-hermetically sealed, yung mga water pump motors, no? mga blower motors, mga iba't ibang motors basta hindi hermetically sealed like aircon, ito yung treatment natin. Okay? So same pa rin sa conductors, magkaiba lang doon sa overcurrent protection, no? So meron tayong peg table na nagagamitin, no? So ito yung consideration. By the way, itong table na ito, maximum rating ito ha. Hindi ito ibig sabihin na ito lang talaga yung multiplying factor na is maximum. You can go as less than these values stated in this table. So for example, we have a AC polyphase motor or three-phase motor, no? Na hindi wound rotor. Yung mga induction squirrel cage type lang na motors, no? Na yung ordinary nga design A. So kung non-time delay fuse yung protection mo, i-rate mo siya up to 3 times. Up to ha, not 3 times, up to 3 times. So pwede kang 2 times or 2.5 times. So ang implication nito is ito. Dapat mag-conduct talaga tayo ng coordination study, especially during starting ng motor, no? Na magkano yung starting current niya, then ito yung fuse ko, ito yung characteristic ng fuse ko na ikuan mo yung sa TCC yung pinakita ni Gob Adrian kanina na TCC for the arc flash. So for coordination study, same TCC, i-plot mo yung starting characteristic ng motor mo tapos i-plot mo din yung fuse characteristic curve niya, then i-check mo during starting kung hindi ba magbabangga yung dalawang curves. So pagbabangga siya at 2 times, then you upsize to 2.5, then up to 3. Up to 3 lang, no? Kung non-time delay fuse. Kung dual element fuse, meron siyang slow element tapos may fast, no? Up to 175. Kung instantaneous strip lang na breaker, wala siyang thermal or inverse portion of the curve, up to 8 times. Depende kung but up to 8 times lang. Kung pwede siyang i-adjust to 6 times of the FLC, then hindi siya mag-cause ng or ma-coordinate mo siya, then well and good, no? And then for the inverse time, yung mga breakers natin na talagang thermal magnetic, may thermal tsaka may magnetic na element, then up to 2.5 times. But you can go as much as 2 times, as low as 2 times, or 175 times, no? Walang kuan siya, wala siyang fixed na kuan. So, as long as ma-coordinate mo lang siya during starting, no? Okay na yan. But not to exceed the values in this table. Yun lang ibig sabihin dito ng table. So, you have to know ang type of motor mo, and then know also, ano din yung specify mo na type of circuit breaker, no? Is it instantaneous strip only or inverse time ba or the fuses ba na type? Okay. So question from Sir Jason, no? Okay. Anong treatment po for same rating motor loads? 230 horsepower kung sabay silang andar. Same din sa 15% of the okay, so I would presume that ito yung combination of motor loads in one circuit ba ito, sir? No? So uh, ideally po, wag mong pagsabayin sila So ang kuan din is 125% of the highest motor load or one of them kung identical, then plus the sum of other loads. Meron tayong competition mamaya, sir. Pakita ko lang mamaya yung combination of motor loads, okay? Sige, to answer fully your question po. Okay. Sige. So, examples lang ito kanina yung discuss natin, no? As long as hindi lang lagpas ito yung maximum multiplying factors natin, ha. But again, we have to do especially for larger motors, no, yung mga malalaking motors talaga na hindi ka na certain na yung i-assume mo na multiplying factors is coordinated ba talaga, then you have to do coordination study. Yun lang yung implication nito, no? Especially for industrial plants, dapat coordination study ka sa mga malaking motor. Yes, yung mga 2 times enough na. Wala akong nakaproblema, no? Yung mga maliliit lang na motors, no? But for really big ones, we have to do coordination study. Okay? So that's for branch circuit, no? And now for feeder and sub-feeder circuits, again, para madali tayo, the same treatment pa rin, but the difference between feeder and branch circuit is the feeder circuit is now a combination of those branch circuit loads. I-total mo lang yung mga amperes nila, no? Yun ang difference ito. And then the application of demand factors, no? Yun lang difference ng na pumasok na sa demand factor, no? And then combination of all those loads na yung sa feeder natin, no? So as you can see in the equation, parehas lang talaga lahat, no? Okay. So sa demand factors, okay. Meron yung binigay si PEC natin, especially for lighting loads na demand factors, no? So meron siyang binigay for different type of occupancies. And mayroon siyang iba't ibang consideration, no? For example, dwelling units, no? So for the first 3 kVA, no, na load, no, it's considered as 100%, no? Kung ang total demand mo is, for example, 10 kVA, no? Meaning to say, ang 3 kVA niyan is 3 kVA. Huwag mong gagalawin. Then the remainder of that 10 kVA, which is the 7 kVA, no? Yan, applyan mo na ng 35%. So meaning to say, 3 kVA plus 35% of 7 kVA, yun na yung demand mo na applied with demand factors. Yun yung ibig sabihin yan. Okay? So, use this one po. Huwag tayong mag-magic-magic ng demand factor, no? So, ito yung gagamitin talaga natin. Then, that's for dwelling units. For hospitals, ito rin. Iba din siya, no? So, 40% yung kuan niya. The first 50 kVA, no? So, mas kuan yung demand factor kay hospital. So on and so forth, no? So, makita mo itong table na to sa PEC natin. Okay? So, use this one po. Kung talagang gusto mong maglagay ng analysis paano na-derive yung demand factor, ito yung process natin. Okay? Okay, so for GPRs, no? So, permitted to be made subject demand factors given sa dito na table, no? Okay, ito yung sa mga outlets natin. Okay. So, for non-dwelling ito meaning to say yung mga commercial, no, banks, offices, basta anything non-dwelling, ito yung kuha natin, no? So for the first 10 kVA, 100% talaga siya. Then the remainder would be 50%, no? For dwelling units, pwede kasi nating isabay si outlets, yung ordinary outlets natin doon sa demand factor calculation doon sa lighting. Yun yung kuan sa mga dwelling units natin, no? So kaya nga hindi masyadong kuan si kuan si dwelling units, no? Ah pwede nating isabay siya doon, no? But for non-dwelling, ito yung gamitin natin, no? So ito yon, no? The receptacle loads are added to lighting load, no? If applicable, ito yon sa mga dwelling units, no? Sa mga non-dwelling units, ito yon. Separate talaga. So these demand factors do not apply to outlets based on 2.20 or yung banks and offices, no, for land dwelling. Okay? Sa motor load demand factor, okay, meron tayong table diyan, no? Ito for uh, hermetic refrigerant compressors, no? Mga aircon loads, no? So, air conditioning equipment, no? Usually demand factor natin yan is 100% of the load, no? So, kung combination of loads yan, okay. So, first 8 kVA of all other loads, kung 8 kVA siya, for example, 10 kVA yung total mo, including air conditioning equipment. So, ang 8 kVA yan is 100%, then ang 2 kVA is 40% na lang, no? So, ito yung treatment natin sa mga air conditioning loads and other space heating loads, no? Small appliance, okay. Ito yung sabi ni Sir kanina, no? Small appliance circuit loads, yung dedicated loads 1,400 volt amperes for each 2-wire small branch circuit. Okay. So where the load is subdivided through 2 or more feeders, so the calculated load for each shall include not less than 1,500. Okay, so kung mag-subdivide siya, dapat ang load natin same pa rin, no? Not less than 1,400 amperes for each small appliance branch circuit kahit pinaghiwalay natin, no? Oops. So for appliance loads in the dwelling units, it shall be permissible to apply a demand factor of 75% to the nameplate rating load of 4 or more appliance. Okay. So kung meron tayong sa isang circuit, no? Uh, or sa isang panel board, no, na 4 or more appliances na dedicated or fastened in place. So pwede nating applyan ng 75% a total of those fastened in place. So for example, kung ang total mo sa fastened in place is 100 kVA, no? So ang i-apply, kung mag-apply ka ng 75% to the nameplate rating load of 4 or more, no? So 75% of 100 kVA. So 70, ang kuan mo lang is magkano na 'yan? Basta lesser na, no? At mga 20 kVA na lang siguro ang kuan mo, ang i-declare mo na demand niya pag 4 or more loads na. Okay, so sa welding machine, sir, meron tayong table diyan. I-quad ko lang dito kung magkano yung sa 2 or more, no? Meron tayong table diyan. Hindi ko nasabay dito, I will just add that, no? Okay. So, kung for kitchen equipment, meron din tayong table dyan, 2.20.3, no? Uh, this demand factor should be applied to all equipment that has either thermostatic control or intermittent use, okay, as kitchen equipment. Pero hindi ito applicable sa mga space heating, ventilating, or aircon. So, for kitchen equipment na talaga itong table na ito, no? So, ito, for kitchen equipment other than dwelling units. So, kung mga restaurant yan, ito yung gamitin natin, no? If we have 2 kitchen equipment, so 100% yan of those loads, no? Pag more than 2 na, up to 3, apply natin na 90%, so on and so forth. Okay? So, ito yung guide natin for kitchen equipment. Okay, good question, no? Kung sa mixed use, saan mag-govern yung demand factor? Actually, sir, i-separate mo talaga yan for mixed use. Separate demand factor for dwelling, separate demand factor for commercial. And then you combine that, no, dun sa main. Yun yung treatment dyan. Hindi yan which over the other, no? Treated separately yan, no? And then i-overall mo lang demand factor later on doon sa main feeder natin. Yun yung treatment po sa mga mixed use. Okay. Okay, so let's proceed. So for feeder circuits, pinagkuhanan ko lang dito. Again, like I said kanina, same equation doon sa branch circuit with the exemption of the application of demand factor. Yun lang diferensya talaga. Okay? Same pa rin dito sa circuit breakers. Demand factor pa rin yung diferensya, no? Same consideration pa rin the next higher standard rating. Okay? For motor loads, same pa rin, no? But ang diferensya na is ito ha. So the one now is the sum of the full load current ratings of all the other motors. Ito yung one considerations. First consideration is 125% full load cost yan. Second, sum up the rest of the motor loads, no? Their full FLC. And then next, kung may combination yan na non-motor load, so 100%, i-add mo lang yung consideration natin sa non-continuous and continuous motor load, no? So, in summary, ito yung formula niya, no? 125% of the highest motor load plus some of other loads, either non-continuous, non-motor load, and then 125% of the by the way, i-kuhan ko muna yung formula, no? So basta the thing is highest motor load times 125% plus sum of other motor loads. And then ito yung 3 and 4, no? So ma-follow rin 'yan. Okay. So for motor protection, ito yung kaibahan, no? Now, for combination of motors, no, for feeders, ang circuit breaker natin for feeder circuit breaker, ang first consideration na is no longer the amperes but the rating or setting na of the protective device, no? Ito na yung kuan na. Then plus the sum of the full load currents. So in equation ito na. Sa circuit breaker feeder natin, hindi na ito current ha, but the circuit breaker rating na. So kung ano yung na identify mo na circuit breaker rating doon sa particular motor, yung highest motor mo, doon yun na ilagay mo na value. Hindi na yung current niya, but the circuit breaker rating. That is as per code ha. And I know the wisdom because this is for coordination purposes, no? Coordination purposes na ito para ma-ensure talaga na during startup of this big motor, hindi ito magti-trip. And during startup na may loaded na siya and then biglang papasok si pinakamalaking motor, it's guaranteed na, or it's not really full guarantee, but at least uh, it can give you an opportunity na hindi ito mag-noise sa stripping, no? Kaya nga ginamit yung circuit breaker rating na, not the full load current, no? Okay, yun lang diferensya sa mga motors. Okay. Okay. So ito yung combination ha. Okay. So ma-follow mo lang yung equation na ito, no? Sum of other loads. Okay. So that's our design considerations. Now in application, ito na. So first, yung load density, no? So ito na yung actual calculation natin. Balik tayo doon sa from the very beginning, paano natin i-develop, no, from scratch to load schedules. Okay. So establish the demand load requirements, no? So firstly, we deal with the lighting loads, no? So gamitin natin yung table 2.20.3. So then the receptacles, then so example nito, no? Ginamit ko lang yung IIEE Cebu chapter office, no, for simplification. So ang total square area dito sa office is 70 square meters. So let's calculate first for the total lighting demand, no, for the office. So anong given area? 70 square meters. Anong type of occupancy? It's an office. So to establish lighting load density, let's look at table 2.20.3. So, ito, office buildings, no? So ano yung load density niya? It's 28, no? Volt amperes per square meters. Okay. But again, I've included also other references just to compare, no? So I have this from ASHRAE, IES. So meron din silang ibang recommendation for offices. Actually, it's in English units, no? So meron silang range, no? Per square area, no? So yung office ng Cebu chapter, it falls between this range, no, from 2001 to 10,000 square foot, converting that to square foot, no, yung 70 square meters. Okay, so meron akong piniselect ko itong 1.81, no, na load density, no, volt amperes per square foot ito. Okay. So i-compare natin yan mamaya, no, kung magkaiba ba or magkatulad ba. Okay. Kung sa pec table natin gamitin, ito yung demand natin, no? 1960 VA or let's round off na lang to 2 kVA. Ito yung total lighting load demand. Now for outlets, same data. Okay. Ito yung general purpose receptacles, ha? Okay. Now, the problem with outlets is yung non-receptacle type, walang binigay na table si PEC natin 2017. So I've sourced out other references for this one, particularly IEEE standard 241, no? So ito, no? General purpose receptacle outlets, excluding ito yung mga air conditioning heating equipment. Now, meron siyang pinarecommend na low density. Meron itong kwan, occupancy density, no? Low, high, average. So really depends na ito. Ito yung portion na ito, engineering call mo na ito kung ano i-assume mo or i-communicate mo ito sa client mo kung anong expected na occupancy nito. Is it going to be a high density occupancy or low or average? So for conservative, pwede mong gamitin si high, pwede mong gamitin si average, no? So let's just try the average, no? Occupancy density. Okay. So again, applying that formula, no? Although we can also apply the 180 volt amperes, but again, we need to establish, no, the number of outlets dyan, no? So let's just try muna dito. Okay, so I've tried a occupancy load density of 1 VA per square foot, converting that to square meters. So it's 10.76 VA per square meters, no? So multiply that by the square area. So we have a computed load density for outlets at 753 VA or 0.753 kVA. Okay. But then again, please keep in mind yung density calculations, low density natin calculations is just for average net demand of the office, no? Now, the problem is this one. Like I said, there's a design stage process. Now, during the design stage na talagang na-establish na yung how many outlets ang needed for this office, no? Actual requirement na talaga, we have to then compare, no, our assumptions to the actual load that is going to be used. Okay, now, meron tayong assumption na 180 volt amperes, no, for each receptacle if up to 3 gang, no, and 90 for 4 gang or 360 VA for a one receptacle nga for kuano. So we will suspend this later on, no? Kasi i-establish muna natin yung comparison between load density and the actual connected load, whichever is higher. Okay? So skip muna natin ito. Then let's go muna for air conditioning loads, no? For this one, normally we need talaga sana the data from our mechanical engineers, no? What is the demand for the aircon or computed na talaga nila, no? How many lang gusto kayong or references na pwede natin magagamit. Same resource table 6.14. So ito yung table na ito, no? So for an air-conditioned area, there's a specific type of occupancy also or type of building, and then there's a low density table, no? So for the office buildings, PA per square foot, no, yung low density. Okay. This is the calculations, okay? How much is our total demand? It's 7.27 kVA. Ito yung low density ha, na assumptions natin for the office building of Cebu chapter. Okay. But then again, during the final stages of the design, wherein nakuha na natin yung mga data from other engineering disciplines, we have to compare. Paano natin i-distribute yung currents in a three-phase bus and having single-phase loads, no? Ito yung circuit arrangement actual talaga sa bus barring. Okay, so leave it muna, ito yung demand natin, no, as of now. After the next step, let's now compute for the number of lighting, how many branch circuits ang needed natin for that demand. Okay, so we have the lighting load demand na of 2 kVA, and then system voltage natin is 230 volts. So how many amperes yung total natin needed is 8.69 amperes, di ba? So if we are going to specify a 15 ampere lighting outlet circuit, how many lighting devices ang pwede nating ipasok? Or how many lighting circuits ang needed natin, no? Keep in mind na hindi natin pwede i-load siya beyond 80%, ha? So yun yung kuha natin, no? So 15 amperes divided by 8.69 amperes yung demand current natin total. How many circuits? 1.72 circuits. So wala tayong 1.72 circuits. Let's start off to 2 lighting outlet circuits, no? So meaning to say, yung current mo for each circuit is divided by 2 na. 8.69 divided by 2 is more or less mga 4.3 something amperes. So medyo malayo na yan sa 80% of the 15 amperes. By the way, magkano pala 80% kasi continuous load is lighting, eh, no? So just to check, no, kung hindi ba tayo nag-violate, no? So magkano si 80%? It's 12 amperes. So malayo-malayo pa talaga, no? So safe tayo. So a minimum of 2 lighting outlet circuits is needed, no, for this demand. So but sometimes uh, best practice dictate sa inyo na yan, no, kung okay ba yung 2 lighting outlet circuits in terms of reliability. So sometimes you may also recommend 3 lighting outlet circuit para hindi masyadong maraming ilaw na madadamay, no? Kung just in case lang na papalyar si isang circuit o dalawang circuit. So ang sabi lang nito, at least 2 is required, but you can have as much as you can. Basta i-balance mo lang yung cost din and reliability. Okay? So inyong call na yan. Okay. So again, pag gusto ko ng 3 circuits, then the demand now per circuit is bumaba na, 600 na lang per VA. So current for each circuit is 2.89 amperes. So walang problema talaga. So kung gusto mo mag-add ng additional lighting circuits, pwede pa. No? So meron kang allowance na. Okay? So ang calculation ko dito, wala akong nag-apply ng derating muna, ha. It's considered na standard yung installation natin na not more than 3 conductors in a raceway at yung ambient natin is relatively nasa standard ambient temperature of 30 degrees, no? Wala. But anyway, kung certain conditions dictate na mag-derate tayo, like for example, more than 4 conductors yung pinahatak mo sa installation, then apply the appropriate derating factor. Meron tayong table dyan sa PEC din, no? So ito is assume lang na walang derating applied, okay? But again, as best practice, I would not recommend installing more than 3 conductors in a raceway para hindi tayo magka-problema sa derating, no? So kung bagong installation yan, then why do we have to subject it to derating if pwede naman nating standardize yung installation natin? So the only time lang na mag-apply tayo ng derating kung yung adverse conditions, yung ambient temperature talaga, like on the ceiling or may areas na travel yung o mag-traverse yung raceway natin na in an area na may elevated yung temperature like in the boiler room, then that's the time na mag-apply tayo talaga ng derating. But otherwise, standard installation dictates na wag nating more than 3 conductors yung isang conduit natin, no? Yan yung practice na yan na minsan sa mga practitioners natin para lang makasave ng conduits, but it is not it's not worth it, no? It's not worth the headache na mag-apply pa tayong derating. Just follow na lang the standard conduit fields or no, para wala tayong as much derating as possible, no, na ilalagay. Okay? So ito, binigay ko na yung reference ito. I know a lot of you are very familiar with this ampacity table natin, no? So just a review lang na meron tayong tables for ampacity. If meron kayong suppliers ng ng tables ng manufacturers natin, specific table of their capacities, then use it, no? If meron, like Phelps Dodge, palaging nabibigay yan ng capacity table ng cables nila, then use it, no? If wala tayo dyan, then you can use the PEC, no? This one, TW, with its temperature rating, 60 degrees, 75 degrees, and 90 degrees. Okay? So just select appropriately na lang, no? But then again, temperature matching is important, no? If you specify TW, or if your circuit breaker is rated temperature at 60 degrees, then you'll be using a THW kasi mas malaki siya ng ampacity because of its insulation, but yung breaker mo is 60 degrees pa rin, you cannot use the 75 degrees stable ampacity. You're still going to use the 60 degrees stable, no? So, wag mong i-assume na kasi 75 degrees yung cable mo, automatic itong column na ito yung gamitin mo. No. Kasi yung circuit breaker mo is limit lang to 60 degrees. So you have to match that para hindi magka-noise and stripping. Otherwise, you specify a 75 degrees na circuit breaker na temperature rating niya. Okay? If you really want to use THW. But then again, cost difference, no? Mas mahal kasi si 75 degrees. But let's just standardize na lang yung practice natin. No? Huwag tayong mag-exhibition, no? Okay. So ito yung standard table. Sinabi natin kanina yung mga next higher standard size, paano natin. So meron tayong guide, but then again, be mindful also that some of these ratings are no longer available in the market, like the intermediate sizes, no? The 25, the 35, the 45, wala na yan, no? So it's also worth it na you verify kung yung mga ratings na ito is nandyan pa ba rin, no? If not, then you decide, no? Whether is it worth it to use the next higher or the next lower, no? Or ihabulin mo lang yung capacity ng cables natin. Okay? So for example, ito, no? Yung kuha natin kanina, so if we're going to use 2 mm squared because ito yung it can already handle the load, no? So just keep in mind for temperature matching purposes, use circuit breaker rated at 60 degrees or higher. Pwede rin higher, no? Kung para ma-address yung quad, but it's not necessary. Or if you're going to use 3.5 mm squared, then use 75 degrees. But if you're going to use THW 75 degrees, then your circuit breaker 60 degrees, please make sure yung opacity table na ginamit mo is at the 60 degrees table, no? Yun lang ibig sabihin nito. Okay? So, I think hindi ko na i-discuss itong formula, self-explanatory na ito, no? You can follow this one, no? Wala naman, if you can see yung lighting loads natin na circuit, wala yung continuous load, no? Wala yung non-continuous kasi walang outlets doon. So, lighting lang. So, 2.89 times 1.85, arrive ka ng 3.61 amperes. So, maliit lang talaga. Okay, no problem. And circuit breaker, pwede mo nang i-match. Alam natin, minimum is 15 amperes in the market. So, walang problema na yan. No? Properly protected na yan. Now, for outlets, so ito yung demand natin kanina, established demand, 0.75 kVA. Now, the problem is, during the later stage of the design, nagbigay na or na-establish na yung required number of outlets talaga. 23 sets or 23 outlets you needed. Now, dito na magagamit natin yung 180 volt amperes. Now, let's see whichever is greater. Now, for the 23 outlets required for the office building at 180 volt amperes, it will yield a total demand of 4.1. Now, whichever is bigger, the load density or the actual load. In this case, mas malaki si actual load. So, which yung gamitin natin? Si 4.14 or the actual load, di ba? So talaga yung mas malaki. So during this stage, mag-validate na tayo, no? I-adjust na natin yung design natin. Okay? So next, ito na, computing na for load current, no? For each circuit, no? So or circuits muna, how many circuits? Okay. So for the 4.1 demand at a system voltage of 230 volts, yung demand current natin is 18 amperes, no? So minimum number of circuits 20 amperes. So it's 1.38, no? Kasi may ilagay tayong 0.8 pero pwede namang walang 0.8, no? Just in case lang gusto ka ng allowance. So pwedeng one or two circuits actually, no? One or two circuits, no? So how many outlets per circuit? So kung two circuits yan, then there are 12 outlets per circuit. So for 20 amperes na provision, like we have a limit of 13 outlets ba yun, di ba? So kung ayan tayo, 12 outlets per circuit. So yun lang consideration natin, ha. For a 20 ampere circuit, up to 13 outlets lang tayo. For 15 ampere circuit, up to 10 outlets lang. Hindi kasi dahil kaya pa rin ni circuit, but meron tayong sinunod na limit of number of outlets per 20 ampere or 15 ampere circuit. So dapat i-consider pa rin yan. Okay, so 12 outlets comply. So let's move total kVA, no? And then load current per circuit is 59 amperes to size up for the wire, no? And then is 9.39 amperes. So ano yung size of wire natin? For me, for outlet circuits, no, for home run, I would specify not less than I would still use 3.5, no, for outlets GPRs, no. So same principle pa rin, temperature matching natin. Okay? Then for circuit breakers, alam natin 20 amperes yung pinaspecify natin. We can go as low as 15, we can go as high as 20 amperes. But then again, I have to correct this one, no? It's 20 amperes pala because it's 12 outlets na per circuit. So I will have to edit this one, no? Hindi na ito 15 kasi lagpas na tayo sa 10 outlets na limit for 15 ampere circuit. So I will edit this one to 20 amperes, no? Okay, just to be consistent with the code. Okay. So for air conditioning branch circuit, so isang con with a total demand or with a demand of 2.76 kVA with power factor and efficiency considered na dito, have a table of FLC with 2 horsepower sa table has a FLC of 12 amperes. So ito yung gamitin natin for computation. Okay. So for aircon motor circuits, no? Again, ang yung kuha natin kanina is 175% minimum multiplying factor. So yung motor kuha natin is 21 ani, diba? Yung conductor muna pala, sorry ha. So 125% times 12 is 15 amperes, no? So let's look at the table. Ano yung conductor natin? So I use 5.5 square meters, no? At 60 degrees even for 75 degrees. Okay. So pwede na namang gamitin yung 3.5, no? Really your choice, no? Okay. So for the motor circuit breaker rating, 175% times 12 is 21 amps. So again, the question, should we use the next size higher or the next size lower? No? So if we're going to use the next size lower, the problem with that is we might not be able to coordinate the motor during starting, no? So it could trip, no? It could cause noise and tripping. So that's a problem now. So we're going to use the next size higher Are we allowed? So again, the condition would follow, no, like it's only a one load, no, per circuit, no, isa lang siya. So predictable, and then it also has its own overload protection yung motor natin, yung aircon natin. So no problem with the overload protection. So our circuit breaker now acts as a short circuit and ground fault protection na ng circuit natin. So we can use the next size higher, walang problem yan, no? As long as within pa rin yan doon sa limit, no? Magkano ba yan? 40 divided by 30 divided by 12, no? Hindi ba yan lagpas sa 2.5 amperes, 250%? Tingnan natin, ha? Tamang-tama lang, no? The 30 amperes is 2.5 times dun sa FLC natin na 12. So within pa rin. So we can use that, no? So no problem. Okay. So 30 amperes is it, no? Okay, so for motor load na non-hermetic ito, no? So it is this rating 1.84 kVA, again all other factors considered. So looking at the spec table, it has a full FLC of 8 amperes. So FLC times 125% for sizing our conductors is 10 amperes. So we can use 3.5 mm squared, either TW or THW, no? And then for the circuit breaker rating is 2 times, ginamit ko lang si 2 times, no? It's 16 amperes. So walang 16 amperes in the market. So ano yung gamitan natin is 20 amperes. Just check lang si 20 amperes if it's going to exceed the 2.5 times, no, allowed. Okay, again, let's check. So still within or perfectly 2.5 times, no? So diyan lang pag-evaluate, no, na if okay pa ba the next size higher, no? So it's still within 2.5 times dun sa FLC. So protected pa rin yung kuha natin sa short circuit and ground fault. Okay? Yung kuan sir, kung mas maliit, ang kuan natin is talagang yung the biggest kasi yung circuit yung sinize up natin sir, no? Yung full load ampere nameplate, ang protection sa motor niyan is yung overload relay niya, no? Ang sa short circuit, ang sa circuit breaker natin is protection ng circuit natin including conductors from short circuit and ground fault na, no? So walang issue kung malaki yung difference between the table and the motor load. The issue lang siguro is the cost, no? The issue is the cost, no? Yan lang siguro. But we have to explain lang talaga na uh, yung kuan kasi, yung code natin nag-specify whichever is higher. So dapat ikuha natin sa stakeholders natin, no? Okay? No, may question pa ba? Sige po. Okay, let's proceed, no? So that's for branch, no, circuit calculation. Okay, for line conductors. Now for equipment ground conductors, no, hindi ko na lang ito i-expound further. Alam na natin yung function nito. What are they for? No, it provides a ground fault path back to the source during ground faults, no. So kung wala si equipment ground fault, wala mangyayari sa breakers natin during ground fault. Hindi siya magti-trip. So exposing again our personnel to shock hazard, no. So that's the importance of and then we have to properly size our equipment ground conductors na it could carry or has a very really low impedance, no, going back to the source para mas malaking current yung dadaloy sa kanya, and our circuit breaker can see that fault current. Kasi pag hindi yan makikita ng circuit breaker natin, maliit lang yung current na dadaloy during ground fault, wala mangyayari sa breaker natin, hindi yan titrip. So dapat i-address natin yung enough ground fault current na makapag-trip ng circuit breaker natin. And the problem sometimes, kung hindi appropriately size yung ground conductor natin, no, malaki yung impedance. So, we know naman kung malaki yung impedance, maliit yung current natin na dadaloy, no? So, ang maka-influence dun sa impedance is the length of the cable and the size of the, or length of the conductor and size, no? So, meaning to say, kung may system tayo na medyo mataas na yung run natin, then we have to conduct na talaga a ground fault study, no? To check on the impedance of the cable, kung enough current pa ba yung dadaloy during ground faults. Especially for high-rise buildings, yung mga malalaking industrial complexes, no? Yung table natin sa PEC may not be enough na. Yung table kasi sa PEC natin may limitation ito, no? But it can simplify our design. Like for example, this one, instead of computing, meron na siyang specify na minimum size of ground conductor for a certain rating of circuit, like 15 amperes. Minimum size niya is 2.0, no? But this can only be applicable for a certain to a certain extent kung di masyadong mataas yung mga length of runs natin ng circuit natin. So, as designer, kung medyo mataas na talaga, we need to really re-evaluate kung itong table na to ng PEC natin is still enough to produce a low impedance path para mas malaking current yung dadaloy during ground fault na makapag-trip ng breakers natin. If not, then problema tayo dyan, no? So ito lang, initial lang ito na sizes, no? So para lang kung ang establishment natin is not that really very big expanse, then this table might be enough already, no? So ang guide lang natin is for certain rating of the circuit, meron tayong corresponding na size of equipment ground conductors, no? So the bigger the circuit, the larger din the minimum conductor size required. Okay? So ito lang table na to, no? So again, hindi ko lang muna ito i-discuss paano yung mga installation methods, no, kasi medyo we are one of time, but I'll just be giving you this guide paano yung mga circumstances, paano kung allowed ba in a cable tray na isang malaking ground conductor lang or dapat pa talaga magkasabay lahat. Ito yung mga do's and don'ts, no? So ito lang isang approach din paano kung biglang linaki yung phase conductors, no, because of voltage drop consideration. So paano palakihin si equipment ground conductor, no? Hindi naman bago yung circuit is 250 amperes pa rin, but binago lang yung or medyo nagbago yung circuit pero not as much as it could permit na kung yung malakihan talaga yung increase, no? So kung wala kang table, pwede mong i-compute paano i-size up si equipment ground conductor from a 22 mm squared, no? Okay. So equipment ground conductor. Okay. So ratio proportion lang, no? So kung initial phase conductor natin is 125 mm squared tapos pinalakihan siya ng 150, original size natin ng equipment ground is 22, ano yung final size natin na ma-match dun sa 150 mm squared? So simple lang, ratio proportion. Magkano yung ratio between 150 and 125 is 1.3 times. So times lang din sa 22 mm squared. So ang result natin is 28.6. So ano yung next nearest standard size is 30 mm squared. So from 22 mm squared, gawin na natin ng 30 mm squared, no? Just in case mag-increase yung circuit natin. Okay? Or look at the table, no? Ito yung conductors in parallel, no? So kung parallel conductors, dapat parallel din magkasabay si equipment conductor. In every set, meron siyang kanyang corresponding na equipment conductors. May exemption ito. Pwedeng isa lang siya na malaki kung in a cable tray. Pero kung isang sa conduit siya, dapat magkasabay. Isang equipment ground conductor sa isang set, tapos sa kabilang set din. Okay? So, I'll just keep this one. Babasahin nyo lang ito, yung mga do's and don'ts kung iba't ibang klaseng installation, no? Okay. Ito pala, no? Importante lang, yung equipment ground conductor, minimum size niya in a cable tray dapat 22 mm squared lang or larger. Okay? We cannot use 14 mm squared in a cable tray. So, dapat ito yung tandaan natin. Okay? Huwag kayong specify ng 14 mm squared in a cable tray. Pwede yan sa raceway or conduits. No? Paano po kung 3 sets? No? How to compute a ground conductor. Okay. So, again, proportion lang natin, sir. Yung circuit natin, initially, tingnan natin yung look-ahead circuit, no? Magkano siya. So, kung ang paralleling mo is, pwede na rin i-kuan mo, uh, yung amperes mo, i-divide mo by 3, no? No? Then ano yung conductor size na appropriate diyan na makakarry doon sa yung kuan mo pag divide ng 3, no? So, for example, kung uh, 150 mm squared, yung 300 amperes instead of isang 150 mm squared, ginamit mo is dalawang 80. Tapos yung dapat na size mo is 30 mm squared, no? Kung divide mo ng dalawa, then ano yung capacity ng 30 mm squared, divide to mo lang, then look for the appropriate size of conductor that carry that current, no? Pretty straightforward lang po yung equipment ground conductor natin. Okay, so tapos na tayo sa lahat ng conductors. Now, the next step is tabulation na of schedule of loads. Okay? So, ito nang next step natin is para to compute na the feeder conductor sizes. Tapos na tayo sa branch circuit, no? So, tabulate everything in the load schedule. Now, for single phase loads na in a three-phase bus, dapat i-balance natin yung distribution ng currents, no? Among the three phases, no? Para mag-balance loading tayo. Okay? Okay, so ito yung example ng demand factor na, no? Kasi patungo na tayo doon sa feeders na, no? So initially, ito yung total connected demand natin, 25.88 kVA. Wala pa itong in-applied na demand factor, no? Okay, so pinag-sum up lang natin. Okay. Now, before tayo mag-compute ng feeder conductor sizes natin, we must conduct analysis on how to determine the demand factor. Okay? Para hindi magic-magic yung demand factor natin, no? So, we have this data, no? So, initially, di ba sabi natin kanina, i-compare natin yung whichever is greater, yung low density method ba or actual loads. No, it's apparent that during the actual loads calculation, mas malaki na come up si actual connected loads versus doon sa load density. So therefore, we will use the actual load na values, no? So 25.88 kVA na. Okay. So that's the decision that we have to make, no? So again, now we in sizing our feeders, we now apply the appropriate demand factor, no? Okay, so first step, get the total maximum demand. So nakita natin kanina yung 25.88 kVA. Okay? So yung total connected demand, yun yung kuha natin, uncorrected, no? Wala pang demand factors, no? Okay. So, total maximum demand is yung corrected na with demand factors na. Yung gusto natin kuhanin natin dito is yung overall demand factor ng isang feeder, no? Kasi combination of demand factors yung gagawin natin, no? Specific for certain type of loads, no? Okay. So, example, kung solving for the lighting load demand factor ng IIEE Cebu office, so kasi yung kuan niya kanina is hindi ka umaabot ng 3 kVA. Magkano ba yun? 2 kVA lang ba? So 100% talaga. So 2 kVA yan. Hindi yan magbabago, no? Okay. duplicate lang, no? Now for outlets, okay. Okay. Na-double na ito, no? Okay. So ito yung actual load natin kanina without demand factor correction. Okay. So now, let's try other setup, no, para makikita natin talaga yung application of demand factors, no. So now we're going to try to add, no, the lighting loads, no, yung lighting outlets pala demand with the lighting demand, no. So ito yung nakuha natin, okay, 9.64, sinama natin yung outlets, no, na demand, no. So with the lighting. Now just to demonstrate lang how to apply the demand factors, let's just say ni-add natin yung outlets tsaka si lighting, no. So yung demand natin is 9.64, ito yung wala pang adjustment. Okay. Now in-apply natin si first 3 kVA, no. First 3 kVA, so meaning to say 9.64 minus 3 kVA, ang resulting ani dito is minultiply natin ng 35% because ito yung remainder, no. So magkano yan? 2.15 kVA na lang. So 3 plus 2.15, so after application demand factor is 5.15 kVA na. Okay? So then for ECU loads, wala tayong magawa nito. Ito na talaga siya, 8.74 kVA, no? And then electric range, no? So 8 kilowatts, first 8 kilowatts is kuha natin ng 80% demand factor, so 6.40 kVA. So ang mangyayari natin para makuha natin yung overall demand factor, i-add natin itong lahat ng kVA natin na corrected, no? So magkano yan is 20.29 kVA. So ito yung maximum demand na natin talaga. So para makuha natin si overall demand factor, so 20.29 divided by 25.88 will yield us a 78% na demand factor. Okay? So ito talaga yung application niya. Paano natin makuha si overall demand factor? Hindi natin ito magic. Okay? Individually, they have to be treated individually. Okay? Mataas na process talaga, but if you care to really go through this process, ma-familiarize mo ito, you'll be talagang accomplishment mo na, talagang ni-apply ko ito ng design analysis talaga, how to arrive sa ganitong demand factor. So maka-justify ako, maka-defend ako bakit ito yung demand factor ko. Unlike doon sa kinapi-paste lang natin, so i-answer natin sa kanila, ito yung ginamit namin sir, ito yung old practice namin, so pinagkuhan ko lang, then hindi yan magkuano. So ganitong analysis talagang ma-justify mo, ma-explain mo sa kanila how did you arrive at that demand factor, no, in this type. So you can work this out, no, get this template, then you can do your own practice, no. Maggawa kayo ng hypothetical loads para lang ma-practice yung how to derive the overall demand factor. Okay, so I hope I've shared something this one. So ito na yung schedule of loads na tabulation, no. So ito yung mga branch circuits kanina na pinagkuhan natin, no, lighting outlets, receptacle outlets, etc., other loads, no. So itabulate natin yan. Kung single phase, walang problema, isang column lang yan sa currents natin, no. Meron tayong kVA, amperes, load amperes, no, so on and so forth, yung ibang details na kuha natin kanina. Now to size up, no, the feeders, so ito yung computation natin, no. Let's just look at the next page lang para mas malaki. Okay, so yung panel board natin ngayon is a combination of loads. Merong motor, merong lighting, merong outlets. Okay, so how do we sum them up all together? Okay, so this is it, no. Kung combination of loads natin is isabay natin lahat ng formulas na natutunan natin kanina. So first is 125% of the largest motor, no, or full load current of the largest motor. So ang largest motor natin is yung 12 amperes. So 125% plus the sum of other loads, either continuous and non-continuous, no? So kung may motor loads ka, isabay mo na rin dito. But yung i-multiply mo ng 125% is yun lang continuous load. Ano yan? Lighting, no? So 125, itong 8.68 amperes is lighting load ito, plus the sum of other non-continuous loads, no? Outlets, okay? Bakit may minus 12? Okay. Kasi tinotal ko ito, then para hindi magkadoble-doble yung kuan ko dito kasi na 12, si 12 nandito na eh. So itong si 116.44, itong dalawa ito is total na kasabay si 12. So minus 12 ko para hindi ma-doble si 12. Then dito na ilagay natin si demand factor. Wag ilagay si demand factor yung sa multiplying natin na largest motor, ha. Dito siya sa sum of other loads natin ilagay si demand factor para hindi madigate yung multiplying factor dito. Okay? So resulting 104 amperes, no? So looking at the table, we need a 38 mm squared, either THWN or THN, no? And then for the circuit breaker, no? Since this is a combination of loads, I am not allowed to use the next size higher. So I'll be using the next lower size. Ito, no? So kaya nga 100 amperes yung nilagay ko dito. Okay? So ito yung kuha natin, basis talaga natin, no? Okay. So ito yung single phase system for line to neutral loads, the same treatment pa rin, no? Magkaiba lang ito kung sa three phase na, no? So other example ito for three phase design analysis. So just look into this one kasi we are really running out of time. So kayo na lang kuha, no? By the way, in the bus distribution, ito yung distribution ng single phase loads, ha, para hindi magkalito-lito. So for circuit 1, ang connection niya sa bus is AB. Circuit 2 is AB pa rin. Circuit 3 is CA, so on and so forth, no? Just look at this figure lang para hindi tayo magkalito-lito, no? And then how do we, so ito yung kuha niya in a load schedule. Ito yung current distribution niya. Circuit 1 and 2 is AB. Circuit 3 and 4 is CA. Circuit 5 and 6 is BC. So on and so forth. So it's a cycle lang yan, babalik-balik lang yan. Pero ito talaga yung arrangement niya, no? Actual yan, ha, sa bus talaga ng manufacturers natin. So ito yung pag-distribute ng load currents natin sa single phase in a three phase bus para maka-balance tayo. Okay? So ito yung mga ibang conditions lang, no? Anong treatment kung si largest motor is a three phase. Okay, so kung three phase system yan, kung delta connected loads, ang kuha lang natin is meron tayong factor of square root of 3. Ito si 1.732, no? Si 1.732. Okay. So same treatment pa rin, no? Ang kuha lang natin is yung all of the single phase loads, i-convert natin to three phase current, equivalent three phase current. Si 22 amperes, wala nang square root of 3 kasi 3-phase current na yan, si 22 amperes. Ito lang single phase currents, no? And now, for the circuit breaker rating pala, no? Kung meron tayong other motors na kasama dito, you can see, hindi na 22 amperes yung inilagay ko. It's a 60 amperes na, no? Ito kasi yung rating ng breaker natin, 60 amperes. Kita nyo dito, oh. So ito yung ginamit ko, 60 amperes, hindi na 22 amperes. Ito yung pagkabantayan natin, ha? No, so hindi na ako nagamit ng 2 times 22, but diretso na 60 amperes. And the rest same formula pa rin, no? So follow pa rin next lower standard rating kasi pwede naman tayo next standard, but i-upsize din natin si 30 mm squared, no? Ikuha natin siya sa 38 mm squared kung gusto natin gagamit tayo ng 125 amperes, no? Okay? So ito lang yung ibang scenarios, no? What if nandito siya sa phase current? So alam naman natin ang representation, ang kunin pala natin nito is the highest phase current, ha? Kung kung three-phase motor, three-phase system. So, meaning to say, anong highest phase current natin dito is 46, no? So, si 46 lang talaga ang gagamitin natin. Di natin i-add yung tatlo, ha? Si 46 lang. Then, square root of 3 times square root of 3. For delta connected loads ito, no? Okay. So, again, kasi si motor load is nasa highest phase current, so kaya nga deduct ako ng 40 dito para hindi madoble siya. Kasi nandoon siya sa highest phase current sa 46, no? If wala siya doon sa highest phase current, then hindi ito i-deduct ko ng 40, no? May instances kasi na si highest current natin motor load is wala doon sa highest phase current din. So ito yung circumstance na ito, no? Okay. Okay, I will give that kuan po sir, yung 80%, no? Thank you for reminding. Hindi ko nakasama pala dito, no? Sige. I will include this in the slides. Okay, same pa rin, square root of 3, nandyan yan. Then demand factor is dito lang sa sum of other loads, no? Just reminders lang, no? Dito, bakit may square root of 3? Kasi si highest motor load is not a three-phase motor. So, we need to get the equivalent three-phase current niya. Okay? So on and so forth. Kung the load is not the highest phase, so makita nyo wala akong dinideduct dito na 28 amperes, no? Kasi wala siya sa ang highest phase current dito is 42. Pero si highest motor load is nasa phase 3. So si 28, wala akong nagdeduct ng 28 dito. Kasi si 42 walang 28 diyan, no? So okay lang kasi hindi na doble si 28, no? So if you can get the point na walag lang duplicity of values, no? Okay. Now for three-phase wide connected loads, ang differential lang talaga wala siyang square root of 3, no? So that's the advantage of a three-phase five-wire system. Yung conductors natin is a bit smaller, no? Yung conductors natin na dapat nating gagamitin. So cost efficient siya compared doon sa delta connected loads, no? So ang kuan lang is may neutral wires ka, no? So again, you have to size it properly. For rule of thumb, si neutral conductors is usually the same size as with the phase conductors for kung meron tayong neutral loads, no? Okay? Okay, so yun lang. Ang pagkaibahan lang talaga ni delta connected sa Y connected is si factor of square root of 3. Okay. So just follow everything, no? If you have some you can see some errors, please do call me. Please call my attention, then I will correct it accordingly, no? Sige. So next, tapos na tayo sa load schedule. Na-size up natin si branch circuit tsaka si feeder circuits natin, no? So the last step that we need to do is the sizing of our main switch gears or the transformers, no? So at this portion, dito na papasok si diversity factor, no? So for large systems such as industrial plants, no, appropriate ito si application diversity factor para hindi ma-oversize si transformers natin or yung mga feeders natin. Okay? So, paano siya i-apply? Ito yan. So, typically, may recommended tayong diversity factors for certain type of loads. Yung pinakita ko kanina, no? So, lighting, feeders, power and lighting feeders. Okay? So, for example, ito, no? Meron tayong iba't ibang demands, no? From various for example various buildings, no, in a certain industrial plant, no? So or various feeders, no? Kung yung design natin is pinag-segregate natin si lighting and power, si air conditioning loads and power loads, no? So meron tayong i-apply na diversity factor. Okay. So for example, this one, no? Yung 300 kVA load natin with a demand factor of 80%, so instead of 300 kVA, to 240 kVA na lang siya. No? Nag-apply tayo ng demand factor. Then the second load is a lighting only, no? So demand factor is a continuous load. So wala tayong ikuan ng demand factor, 100% siya. So 100 kVA is 100 kVA. Then the next feeder is a combination of load, power, and then mayroon tayong in-apply na 70% demand factor. So instead of 500 kVA, may 350 kVA na tayo na corrected demand. Okay? So lahat ito papasok dito sa main feeder, no, sa substation natin. Okay. Now, pag i-sum up mo yan, itong tatlong demand na 240, 100, and 350 kVA, it will come up with a maximum demand of 690 kVA, no? Kung ang diversity factor natin is 1. Now, meron tayong pinag-recommend na combination of loads na 1.5 to 2, no? Pag combination of loads yan, power, lighting. So, what is the effect of that? Okay, this one, no? So, kanina, original demand natin is 690 kVA considering applied with demand factors na ito, ha, corrected na ito. Kasi kung walang demand factor, yung demand sana natin is 300 plus 100 plus 500. So magkano yan? It's 900 kVA. Pero since nag-apply tayo ng demand factor, 690 kVA na lang. But then again, we can still utilize diversity factor to further reduce the demand of our system. So, if we use 1.4, recommended kasi yan na combination of loads, no, yung lighting and powers ngayong kanina. So si 690 i-divide pa natin ng 1.4. Ito yung diversity factor na impact, no. So meaning to say, si 690 kVA na demand, we should have used a 750 kVA substation, or kung i-bank mo yan, tatlong 250 kVA. Now ngayon, in-apply natin si diversity factor na 1.4. So, lumiit further yung demand natin to 492. So, instead na mag-need tayo ng 750 kVA substation, 500 kVA substation na lang yung need natin, no? So, ito yung impact ni diversity factor in the system. It further reduces the demand, no? Especially for transformers. As long as we know the type of load that we have, no? Kung combination yan of lighting and power, then we can use more than one na diversity factor. Siguro 1.2, 1.3, 1.4. It's safe to use like that, no? Up to 2 times, no? So, ito na yung impact or benefit of applying or employing diversity factor. So, si diversity factor, hindi natin ito ma-apply sa mga sub-feeders, ha? Doon lang sa mains natin ma-apply natin si diversity factor. Yung sa mga feeders natin, si demand factor yan. Okay? So, yun yung difference ng dalawa. Okay? So, I think this is it for the first part. So, first mic, I would just skim through with the voltage drop. No? Hindi naman masyadong mataas. Kung okay lang, can we extend a few minutes more?
Sige po, okay lang po, Gov.
Okay, okay, thank you po. No? So, we're done with our schedule of loads calculation. Then, for voltage drop, so just to be brief lang, as per Article 2.10.2.2 of PEC 2017, no? Requirement natin to prevent a voltage drop exceeding 3% at the farthest outlet. So dapat we need to limit, no, the voltage drop 3% from the panel board to the farthest outlet, and then totally from the source to the farthest outlet is shall not exceed 5%. So, no? So to illustrate that, ito yung voltage drop limitations natin. So from source to first distribution panel, dapat hindi lalagpas ng 3%. And from the first distribution panel to the farthest load, dapat hindi lalagpas ng 3%. Para masiguro natin na from source to load talaga hindi lalagpas ng 5%. So ito yung dalawang kuha natin dapat i-comply, no? From source to panel less than 3, panel to farthest load less than 3. So guaranteed yan na hindi yan lalagpas ng 5%. Okay? So, anong steps? Basic steps is, unang-una, single line diagram of the system. Kasama na yung cable sizes and lengths, no? And types of conduits and their unit impedances. Okay? Kasi mag-impact si type of conduits sa impedances. if it's metallic or PVC, no? After that, make an equivalent impedance diagram para din tayo nung gumawa ng short circuit calculation. Then specify now the impedances of the cables to their actual, no, to their lengths, no? Kasi si unit impedances is per 305 meters lang yan, no? So we need to convert that to their actual lengths. Then conduct the voltage drop. So yung formula pala natin is the approximate formula ginamit natin, no? Na hindi yung exact talaga, no? So ito yung approximate formula na hindi naman negligible naman yung error niya or difference niya with that the exact. So mas cumbersome or mas kuan talaga si actual, but the value na negligible yung difference, so approximate na lang tayo. Okay? So this is the formula: multiplying factor times the line current, no, times the uh, load power factor or the cosine theta times the resistance of the cable or the cable and the transformers, no, and plus the reactive power factor or sine theta times the reactance, no, of the cable. Okay? Si multiplying factor is 2 kung single phase. Then square root of 3 or 1.732 sa 3 phase. So as you can see in this equation alone, mas mataas expectedly si yung voltage drop ng single phase systems compared sa 3 phase. Kaya nga mas less yung losses ni 3 phase. Ito yung advantage ni 3 phase talaga, voltage drop handling, no? So dito pa lang makita natin sino yung mas mataas. Okay? So ginamit ko din yung Cebu chapter office. Ito yung single line diagram niya. Utility transformer 25 kVA, no, single phase lang system natin. Then service feeder, ito yung size ng cable niya, 50 mm squared, 15 meters. Then yung panel board niya, no, itong main bus, isang panel board lang ito, then branch circuit na diretso to the load, no. So 40 amperes yung branch circuit niya, then yung branch circuit conductor is 8 mm squared with a length of 10 meters. Okay. So with this one, convert natin to impedance diagram at the other side, no? Impedances ng cable, convert na natin, no? So I treated the transformer differently. Ito yung treatment ko kay transformer, okay? So now, to really use, no, the sending voltage at full load condition, kinuha ko muna yung drop ng transformer natin, no? So paano 'yan? So yung meron tayong percent IZ rating ng transformer natin, no? Nasa nameplate 'yan. So yung line to line voltage ng transformer natin i-minus lang natin doon sa percent voltage impedance drop, no? I-convert natin in terms of voltage. So at full load condition, ito yung percent impedance drop niya. So 240 minus this one will get us a sending voltage, effective sending voltage at 235. So bakit ginawa ko ito? Hindi ko ginamit si 240 kasi ginamit ko yung worst case scenario na pag fully loaded yung transformers natin, at least yung makuha natin na voltage drop compliant pa rin, no, at worst case scenario. Kaya nga kinuha ko ito, no. So ang sending voltage ko ngayon hindi na si nominal at 240 but 235, no. Kung 230 yung nominal, then same equation pa rin, then dapat ang sending voltage mo must be lower than the nominal top, no? Yun yung worst case scenario, okay? So ito yung sending voltage ko. Now, solving for voltage drop. So meron tayong impedance values, no? Resistance and reactance doon sa PEC na table natin, no? Ibigay ko yan mamaya in reference. So ito yung resistance ng cable natin at 305 meters, 0.12 ohms for the 50 mm squared cable in steel conduit. And then the reactance is 0.055, no, at 305 meters, no. But the actual length natin is 15 meters and one cable per phase, and then our line current or load current is 95 amperes. Now, first thing we do is convert the resistance at the actual length. So magkano siya? So at 15 meters, hindi na siya 0.12 but 0.0059. Maliit na kasi maiksi lang. Itong 0.12 sa 305 meters ito, no? So one cable per phase. Okay. Reactance same kuan pa rin. We have to convert at 15 meters. So Instead of 0.055, 0.0027 na lang. So maiksi na kasi, no? So next, we substitute in the formula, no? This is a single phase, yung K natin is 2 times the load current, 95, then resistance times the power factor, load power factor natin at 0.8. Kung ano yung power factor nyo dyan, i-adjust nyo lang. Kung 0.95, then substitute accordingly. Then, the reactance times the reactive power factor at 0.6, no? So, solving for that, we have a voltage drop 1. Ito yung from transformer to first panel board or first bus, no? Hindi pa ito yung sa load. So, voltage drop 1 natin is 1.21 volts. So, ito yung table natin ng reactances, no? Just look at this table, meron diyan sa PEC, no? Chapter 10. So, ito yung AC resistance, no? For conductors, not more than 3 single conductors in a conduit, no? So, dapat yung column nyo, kung steel, steel. Kung PVC, PVC. Okay? So, makiibang reactance yan. Kasi si steel, yung reactance natin will react doon sa magnetic kuan ng steel, no? Pero si resistance same pa rin. Si reactance lang yung magbago, no? So, dapat you have to look at the appropriate column, ano yung raceway na ginamit nyo. Okay? Yun lang yung pagbantayan natin. Then, for the voltage drop from the main bus to the load na talaga, ito yung kuha natin. So, ang kable natin is maliit na, 8 mm squared, no? So, same process, convert to the actual length at 10 meters, yung reactances and resistances natin. So, voltage drop natin is 1.49 volts, no? So, now, solving for the percent voltage drop. So, add natin yung dalawang voltage drop. Total voltage drop natin is 2.7 volts. So, percent voltage drop is voltage drop total over V sending. So, 2.7, ano yung V sending natin is 235.68 volts times 100. So, a total of 115%. So, malayo pa yan sa 5%. So, compliant yan, no? Now, for 3-phase, same process. Anong kaibahan? C, constant lang, no? Ang constant is 1.732 instead of 2 times, no? Same process pa rin. Yun lang kaibahan is 1.732, no? So, after evaluating, 1.29% lang yung voltage drop. So, it has complied with the prescribed limit of 5% from the code, no? Okay, so again, after everything is being done, tabulate everything. Ito yung sample tabulation natin. Pwede yung maggawa kayo ng sarili nyo, but importantly yung feeder description, load description, and the rating, current, and the cable or conductor, and the run length, and the voltage drop and voltage drop percent values. So as a summary report doon sa OBO natin or sa DOLE. Okay? So with that, this is it for me. Thank you very much for listening, everyone, and thank you also for the opportunity, no? So hope hindi na masyadong natagalan.